Hello there, and welcome to the Mikey Wild Tales. I'm so glad you're here. Maybe it's been a long day, or maybe you just like to fall asleep thinking about the most extreme and fascinating objects in the cosmos. Either way, tonight's journey is for you. There's nothing you need to do now. Just let your body rest, your mind slow down, and your thoughts drift. Because tonight, we're exploring one of the universe's most incredible creations, the neutron star. We'll journey deep inside these stellar remnants to understand what happens to the force of gravity when matter is crushed beyond all imagination. We'll move gently from fact to fact, learning how these city-sized objects can weigh more than our sun, how they bend space and time itself, and what strange, exotic matter like nuclear pasta or quark soup might exist at their very center. Some things may surprise you. Others may stay with you like a quiet thought at the edge of sleep. And if these calm explorations help you rest, feel free to like and subscribe. It helps others find their way here too. Now, if you're ready, let's begin. Within the immense expanse of the cosmic stage, there are almost no occurrences as breathtakingly dramatic or as profoundly fierce as the final moments of a truly massive star. These celestial titans, brought into existence through the gravitational compression of colossal clouds of gas, live their lives in the fast lane and perish young, at least in the grand scheme of astronomy. While our own sun is destined to burn with a steady glow for roughly 10 billion years, a star possessing 8 to 25 times the mass of our sun will blaze through its entire existence in a mere fraction of that time, just a few million years. Their entire life is a story defined by an unending conflict between two elemental forces: the outward pushing pressure generated by nuclear fusion deep within their cores, and the inescapable inward clutch of their own immense gravity. To fully grasp how neutron stars are born, we must first embark on a journey into the very heart of these stellar giants during their last desperate moments. Imagine, if you will, a star 20 times more massive than our local star, the Sun. For millions of years, this behemoth has successfully maintained a precarious state of equilibrium. Deep inside its core, the temperatures are truly infernal, soaring past 100 million degrees Celsius. This is more than hot enough to forcibly fuse hydrogen atoms together, forging helium and, in the process, unleashing truly tremendous quantities of energy. This liberated energy generates an outward radiation pressure that pushes against the star's own mass, perfectly counterbalancing the gravitational force that is constantly trying to crush the star inward upon itself. But stars of this magnitude are incredibly gluttonous consumers of their fuel. Unlike our sun, which will leisurely spend billions of years transforming its hydrogen into helium, these giants tear through their nuclear reserves at an astonishing rate. The more massive the star, the hotter its internal furnace becomes, and the faster it burns through its available fuel. It's much like comparing a small, steady campfire designed to smolder through the night with a roaring, towering bonfire that reduces massive logs to ash in a matter of minutes. Eventually, as the hydrogen supply in the core dwindles and becomes exhausted, the star confronts its first existential crisis. Lacking the outward pressure from hydrogen fusion to support it, gravity starts to gain the upper hand. The relentless pull begins to compress the core, causing it to shrink. This compression, in turn, heats the core to even more extreme temperatures, ultimately reaching several hundred million degrees. At these mind-boggling temperatures, a brand new form of fusion ignited: helium burning. Now, 3 helium nuclei can be slammed together to create carbon, once again releasing energy, and temporarily re-establishing the delicate truce between gravity and radiation. This sequence of events repeats itself in a cosmic pattern of depletion and ignition, a cycle of boom and bust. When the helium is gone, the core once again contracts and heats up, achieving temperatures where carbon atoms can fuse to create neon and magnesium. Following that, neon burning forges oxygen and magnesium. Then, oxygen burning manufactures silicon and sulfur. Each consecutive fusion stage burns at a higher temperature and at a faster pace than the one that preceded it, much like a performance engine being pushed far past its limits, screaming toward its red line. During these final, frantic stages, the star's internal structure comes to look like a gigantic cosmic onion, composed of distinct shells of different elements arranged in concentric layers. The outermost layers still possess unburned hydrogen, while the deeper shells are actively burning helium, carbon, neon, and oxygen, one after the other, moving inward. At the absolute center, the final stage, silicon burning, is churning out iron and nickel. This layered structure is absolutely essential to comprehending what is about to unfold, as it perfectly sets the stage for one of the most cataclysmic events the universe has to offer. Silicon burning signifies the absolute end of the line for nuclear fusion as a viable energy source. When silicon atoms fuse, they create iron-56, which holds the distinction of being the most stable atomic nucleus in all of physics. Iron-56 rests at the very bottom of the nuclear binding energy curve. In simple terms, this means that attempting to fuse iron nuclei together actually consumes more energy than the reaction produces. For the very first time in the star's long life, its core fusion has become an energy drain rather than an energy source. It begins stealing energy from the core. This is the precise moment where the star's story takes its final, violent turn. Without the outward thermal pressure from energy-producing fusion reactions to prop it up, gravity achieves its ultimate decisive victory in their long-running battle. The iron core, which itself typically contains about 1.5 times the entire mass of our Sun, but is compressed into a sphere only about 3,000 kilometers wide, suddenly finds itself completely unable to withstand the crushing weight of its own mass. The collapse that ensues is almost unimaginably swift and violent. In less than 1 single second, the core plummets inward, shrinking from 3,000 kilometers in diameter to just 20 kilometers. During this catastrophic implosion, the core's density escalates by a factor of approximately 100 billion. To try and put this into perspective, if you could somehow compress the entire planet Earth to this same density, it would fit neatly inside a sphere just 200 meters across. As the core collapses, several extraordinary events transpire all at once. The temperature explodes to over 100 billion degrees Celsius, a temperature more than 6,000 times hotter than the core of our own Sun. The pressure becomes so utterly intense that atomic nuclei themselves are crushed together. Electrons are physically forced to combine with protons, creating a flood of neutrons. This process, aptly named neutronization, unleashes vast numbers of neutrinos, which are ghostly subatomic particles that almost never interact with normal matter. The neutrinos generated during this core collapse carry away an almost unbelievable amount of energy, roughly 100 times more energy than our Sun will generate over its entire 10 billion year lifetime. The majority of these neutrinos flee the star within seconds, streaming out into the cosmos and carrying with them vital information about the collapse, information that we can potentially capture and detect right here on Earth. But the imploding core does not shrink away into nothingness. When it reaches what is known as nuclear density, about 2 times 10 to the 14th power grams per cubic centimeter, the neutrons themselves begin to powerfully resist any further compression. They do this through a purely quantum mechanical phenomenon known as degeneracy pressure. This is the same fundamental principle that prevents all the electrons in an atom from falling into the same energy state. But now it is being applied to neutrons that are packed together at this incredible density. The abrupt, jarring halt of the collapsing core generates a powerful shock wave. This shock wave reverses direction and begins to race outward, tearing through the rest of the star at thousands of kilometers per second. This outward blasting shock wave is precisely what we observe as a supernova explosion. The energy unleashed in a supernova is truly difficult to comprehend, equivalent to all the energy our sun will shine for about 10 billion years, all released in just a few seconds. The shock wave obliterates the star's outer layers, heating them to billions of degrees and accelerating them to speeds of thousands of kilometers per second. These outer layers, which have been enriched with the heavy elements forged during the star's lifetime, are scattered far and wide into space. They seed the interstellar medium with the essential raw materials required for future generations of stars, planets, and perhaps even life. The very iron flowing in your blood, the calcium that makes up your bones, and the oxygen you are breathing right now were all forged in the heart of a massive star like this and distributed throughout the galaxy by a supernova explosion. Meanwhile, back at the epicenter of this cosmic detonation, something truly remarkable is left behind. The collapsed core has now become a neutron star. This singular object, containing more mass than our sun, yet compressed into a sphere only about 20 kilometers across, represents one of the most extreme and alien environments in the entire universe. Its surface gravity is approximately 100 billion times stronger than the gravity we feel on Earth. A single sugar cube-sized piece of neutron star material would weigh about 1 billion tons on Earth. The composition of a freshly formed neutron star is unlike anything we could ever encounter in our daily lives. The outer crust is composed of atomic nuclei that are arranged in a rigid crystalline lattice. But these are not normal nuclei. They are far more neutron-rich than any that can be found on Earth. As you journey deeper, the nuclei become progressively more exotic, featuring neutron-to-proton ratios that would be utterly impossible under normal conditions. Deeper still, at densities that approach that of an atomic nucleus, the very distinction between individual nuclei begins to blur and dissolve. Neutrons start to drip out of the nuclei, forming a sea of free-flowing neutrons that is intermingled with the increasingly neutron-heavy nuclei. This region, sometimes referred to as the neutron drip line, signifies the transition from what we might call normal nuclear matter to the truly exotic state of matter that dominates the neutron star's interior. At the very center of the neutron star, densities may escalate to 5 to 10 times nuclear density. These are conditions that push our current understanding of physics to its absolute limits. At these extreme densities, it is theorized that protons and neutrons themselves might break apart into their constituent building blocks, the quarks, creating a soup of the fundamental particles that compose all matter. Alternatively, the intense gravitational field might permit the formation of exotic particles known as hyperons, which contain strange quarks not found in ordinary matter. The magnetic field of a neutron star is another incredible legacy of its violent birth. During the core's collapse, the star's original magnetic field lines are compressed along with all the matter. This compression amplifies the original stellar magnetic field by factors of trillions. The resulting magnetic field can be 1 trillion times more powerful than Earth's magnetic field, strong enough to physically warp and distort the very atoms in the neutron star's atmosphere. This profoundly intense magnetic field, combined with the neutron star's extremely fast rotation, creates one of the most precise timekeepers in the cosmos, a pulsar. As the neutron star spins, its magnetic field acts like a cosmic accelerator, shooting charged particles to near light speed. This process creates powerful beams of radiation that sweep across space, exactly like the beam from a lighthouse. When these beams happen to point toward Earth as the star rotates, our telescopes detect regular pulses of radio waves, X-rays, or gamma rays. Some of these pulses arrive with a clockwork precision that rivals our best atomic clocks. The birth of a neutron star also signifies a victory of quantum mechanics over classical physics, played out on a cosmic scale. In the matter we are familiar with, atoms are composed almost entirely of empty space, with electrons orbiting far from their nuclei. But inside a neutron star, matter has been compressed far beyond the point where individual atoms can even exist. Instead, it is quantum forces that prevent the complete and total collapse into a black hole, thereby creating a state of matter where an entire star, miles wide, behaves like a single, giant atomic nucleus. The thermal evolution of a neutron star, or how it cools down after it forms, tells another fascinating story. Born at temperatures of billions of degrees, neutron stars primarily cool down by emitting neutrinos for the first few thousand years of their existence. These ghostly particles, which barely interact with normal matter, can escape freely from the neutron star's deep interior, carrying away thermal energy. After about 1 million years, this neutrino cooling process becomes less efficient. From that point on, the neutron star cools mostly by radiating photons, light, from its surface. This cooling process reveals crucial information about the neutron star's internal structure. Different theoretical models of this ultra-dense matter predict different cooling rates. Therefore, by observing the temperatures of neutron stars, we can help determine what is actually happening to matter under such extreme conditions. Some neutron stars are observed to cool faster than others, possibly indicating the presence of exotic particles or strange states, like superfluidity, within their interiors. Neutron stars also function as natural laboratories for studying matter under conditions that are completely impossible to reproduce here on Earth. The densities found in neutron star cores exceed any that can be achieved in our most powerful particle accelerators. Their magnetic fields completely dwarf anything we can generate in our laboratories. By studying these incredible objects, we gain insights into fundamental physics that would otherwise remain purely theoretical. The formation of neutron stars is just one of the possible fates for massive stars. Stars that begin their lives with masses between roughly 8 and 25 solar masses will typically end up as neutron stars. However, the exact boundaries depend on other factors, like the star's rotation speed, the strength of its magnetic fields, and its metallicity, or its composition of elements heavier than hydrogen and helium. Stars that are less massive than 8 solar masses do not get hot enough to ignite silicon burning. Instead, they end their lives much more gently, shedding their outer layers to become white dwarf stars. Stars that are more massive than about 25 solar masses may have cores so heavy that their gravity overwhelms even neutron degeneracy pressure. They may collapse directly into black holes, skipping the neutron star phase entirely. The transformation from a living, breathing star into a neutron star represents one of the most profound and dramatic changes in all of nature. In less than a second, matter that once filled a volume of space larger than the Earth becomes compressed into a sphere that could fit inside the boundaries of a large city. The star's rotation rate, which might have initially been a slow revolution once per month, speeds up dramatically as the core contracts. This conservation of angular momentum results in some neutron stars spinning hundreds of times every single second. This entire process of neutron star formation connects the fields of stellar evolution, nuclear physics, and general relativity in intricate ways that continue to challenge our understanding. Each neutron star represents a unique, ongoing experiment in extreme physics, a place where gravity, quantum mechanics, and the nuclear forces all interact under conditions found nowhere else in the known universe. As we will explore in the following chapters, these cosmic laboratories continue to reveal new secrets about the fundamental nature of matter, energy, and space-time itself. The violent birth of neutron stars, occurring through these supernova explosions, has fundamentally shaped the chemical evolution of entire galaxies. These events have provided the heavy elements that are necessary for the formation of rocky planets, and by extension, for life as we know it. Yet, perhaps even more remarkable is what these stellar remnants become. The densest objects in the universe, second only to black holes. They are places where gravity reaches strengths that literally bend space-time and create some of the most extreme gravitational environments we are capable of observing. From their explosive birth in the death throes of massive stars, neutron stars emerge as cosmic beacons, destined to shine across the universe for billions of years. Their steady, pulsing signals mark the passage of time, while their extreme gravitational fields provide us with natural laboratories for probing the deepest mysteries of physics. When we consider gravity in our everyday lives, Isaac Newton's simple formula serves us perfectly well. If you drop an apple, it accelerates toward the Earth at 9.8 meters per second squared. If we launch a rocket, we can precisely calculate its trajectory using the very equations that Newton developed more than 3 centuries ago. But neutron stars exist in a realm where Newton's gravity becomes woefully inadequate. Using Newtonian physics to describe a neutron star is like trying to measure the speed of light with a sundial. To understand gravity in the vicinity of neutron stars, we must completely abandon our intuitive notions and instead embrace Einstein's revolutionary vision of spacetime itself. In 1915, Albert Einstein published his theory of general relativity, fundamentally changing how humanity thinks about gravity. Instead of being a mysterious force that pulls objects together, gravity was redefined as the curvature of spacetime, a curvature caused by the presence of mass and energy. Imagine placing a heavy bowling ball onto a stretched rubber sheet. It creates a deep depression, a curve, which in turn causes marbles rolling nearby to swerve and spiral toward it. This analogy, while not perfect, captures the essential idea of how mass warps the very fabric of spacetime. In most situations that we encounter, the difference between Newton's description of gravity and Einstein's description is negligible. Earth's gravity well is so shallow that space and time remain almost perfectly flat. A GPS satellite orbiting the Earth experiences only minuscule relativistic effects, requiring time corrections of mere microseconds. But neutron stars create gravitational fields so powerful, so intense, that they stretch the very concepts of space and time beyond all recognition. Let's consider the numbers that define a typical neutron star. If you pack 1.4 times the mass of our entire Sun into a sphere just 20 kilometers across, you create a gravitational field that is roughly 100 billion times stronger than Earth's. At the surface of a neutron star, gravity pulls with such overwhelming ferocity that it would compress a human body to the thickness of a sheet of paper in a fraction of a microsecond. But even this staggering number doesn't fully capture the true strangeness of neutron star gravity. The key insight from general relativity is that gravity is not just about the strength of the gravitational pull. It is about how dramatically mass and energy bend the geometry of spacetime. Near a neutron star, this curvature becomes so severe that space and time themselves begin to behave in ways that seem utterly impossible from our everyday perspective. Time itself runs slower. Distances contract. And light itself must struggle to escape the gravitational grip. To visualize this curvature, picture spacetime as a flexible, three-dimensional grid extending in all directions. In empty space, this grid remains perfectly straight and regular. Parallel lines stay parallel, and right angles remain perfectly square. But if you place a neutron star at the center of this grid, everything changes. The grid lines bend inward, drawn toward the neutron star, becoming more and more distorted as they get closer to its surface. This distortion has a profound effect on everything in the vicinity. A photon of light attempting to escape from the neutron star's surface must climb up out of this incredibly deep gravitational well, and it loses energy in the process. By the time that photon reaches a distant observer, its wavelength has been stretched, making it appear redder than when it was first emitted. This gravitational redshift can be so extreme that X-rays emitted from a neutron star's surface may arrive at Earth as visible light. The mathematics required to describe this curved spacetime around a neutron star are far more complex than Newton's simple inverse square law. Einstein's field equations, which describe the relationship between the curvature of spacetime and the distribution of matter and energy, require sophisticated techniques from differential geometry just to be solved. Even with our most powerful modern computers, finding exact solutions remains a significant challenge for realistic neutron star models. One of the most useful approximate solutions is known as the Schwarzschild metric, which describes the spacetime around a massive object that is spherically symmetric and not rotating. For a neutron star, this metric reveals several truly remarkable features. As you get closer to the neutron star's surface, time dilation becomes increasingly severe. A clock placed on the neutron star's surface would be observed to tick noticeably slower than an identical clock situated far away from the star. If you could somehow stand on a neutron star's surface for 1 hour, observers far away would measure that several hours had actually passed for them. This time, dilation is not just some theoretical curiosity. It has real, observable consequences. When we observe X-ray bursts originating from neutron stars, the radiation we detect has been directly affected by this slowing of time. Rapid oscillations in the X-ray flux appear to be slowed down to distant observers, and this provides us with a direct way to measure the strength of the neutron star's gravitational field. The curvature of space around neutron stars also affects the path of light in unexpected ways. Photons no longer travel in perfectly straight lines. Instead, they must follow curved paths, known as geodesics, as they move through the warped spacetime. This effect, known as gravitational lensing, means that we can sometimes see around a neutron star, allowing us to observe emission from its far side, which would normally be completely hidden from our view. Recent observations conducted by NASA's Neutron Star Interior Composition Explorer, more commonly known as NICER, have successfully exploited this gravitational lensing effect to map the hot spots on neutron star surfaces. As the neutron star rotates, these hotspots move in and out of our line of sight. But gravitational lensing allows us to see additional emission that would otherwise be blocked by the star itself. By carefully analyzing these light curves, astronomers can determine both the neutron star's mass and its radius with unprecedented precision. The extreme curvature of spacetime around neutron stars also affects the behavior of any matter that ventures into their vicinity. Particles that are orbiting close to a rotating neutron star experience an effect called frame dragging. This is where the neutron star's rotation literally drags spacetime around with it, like a spoon swirling honey. This effect was predicted by general relativity and later confirmed around Earth by the Gravity Probe B mission, but it becomes dramatically enhanced near the extreme gravity of neutron stars. Frame dragging has significant consequences for our understanding of neutron star systems. Matter that is falling toward a rotating neutron star doesn't simply spiral straight inward. It gets caught up in the star's rotation, forming highly complex accretion flows. The magnetic fields that thread through this infalling matter become twisted and amplified, sometimes launching powerful jets of particles away from the star at nearly the speed of light. When we compare the gravity of a neutron star to that of a black hole, fascinating similarities and differences begin to emerge. A black hole that has the exact same mass as a neutron star would actually have a much smaller radius and, correspondingly, a much stronger surface gravity. The event horizon of a 1.4 solar mass black hole would be located at a radius of about 4 kilometers. This is in sharp contrast to the 10 to 12 kilometer radius of a typical neutron star. This difference in radius has profound implications for the gravitational environment. While both of these objects create significant spacetime curvature, the neutron star's surface remains accessible to observation. In contrast, a black hole's surface lies forever hidden behind its event horizon. We can observe matter crashing onto a neutron star's surface, we can study the properties of its atmosphere, and we can detect thermal emission coming from its crust. A black hole of a similar mass would appear much, much dimmer, revealing its presence mainly through the hot accretion disk of matter swirling around it. The gravitational redshift provides another useful point of comparison. Light escaping from a neutron star's surface typically experiences a redshift of about 20 to 40%. This means that blue light emitted from the surface would appear green or yellow to distant observers. Light that attempts to escape from near a black hole's event horizon experiences an infinite redshift. It becomes so stretched in wavelength that it effectively disappears from our view. These differences are what make neutron stars such invaluable laboratories for studying strong field gravity. Unlike black holes, neutron stars allow us to observe matter under extreme gravitational conditions while it still remains visible to us. We can study how atoms behave in gravitational fields that are billions of times stronger than Earth's, how magnetic fields interact with curved spacetime, and how matter flows in environments where the effects of general relativity are not just minor corrections, but are completely dominant. The precision timing of pulsar signals provides yet another window into neutron star gravity. As these rotating neutron stars sweep their beams of radiation across space, we receive regular pulses with a timing stability that rivals our best atomic clocks. But this timing is itself affected by the neutron star's gravitational field in measurable ways. The pulse profiles, their arrival times, and their frequency evolution all encode information about the underlying spacetime geometry. Binary pulsar systems, where two neutron stars orbit each other, offer particularly rich laboratories for the study of gravity. When two neutron stars are locked in orbit, they create a dynamic gravitational environment where the space-time curvature is continuously changing. Their orbital motion generates gravitational waves, ripples in space-time itself, that carry away energy and cause the orbit to slowly decay or shrink. This orbital decay, which was first measured in the Hulse-Taylor pulsar system, provided the very first indirect evidence for the existence of gravitational waves and earned its discoverers the Nobel Prize. The recent direct detection of gravitational waves by the LIGO and Virgo observatories has opened an entirely new window for studying neutron star gravity. When two neutron stars spiral into each other and finally merge, they create some of the most violent gravitational wave signals in the universe. These signals encode detailed information about how matter behaves under extreme gravitational stress, including how the neutron stars themselves deform as powerful tidal forces stretch and squeeze them. This tidal deformability of neutron stars provides crucial insights into their internal structure and the nature of ultra-dense matter. Just as Earth's oceans bulge in response to the Moon's gravitational pull, neutron stars deform when they are subjected to external gravitational fields. However, the amount of this deformation depends entirely on the star's internal structure and its equation of state. The specific relationship between pressure and density in the neutron star's interior. Gravitational wave observations of these neutron star mergers have begun to place constraints on these equations of state, helping us understand what happens to matter at densities that exceed those found in atomic nuclei. Softer equations of state, where pressure increases slowly with density, lead to neutron stars that are more easily deformed. Stiffer equations of state produce more rigid neutron stars that strongly resist deformation. By measuring these tidal effects in the gravitational wave signals, we can begin to distinguish between different theoretical models of ultra-dense matter. The extreme gravitational fields around neutron stars also serve as natural testing grounds for Einstein's theory itself. General relativity has successfully passed every single test we have been able to devise, but neutron stars push the theory into regimes far beyond those where it was originally verified. The strong equivalence principle, which states that all forms of matter and energy respond identically to gravitational fields, can be tested with exquisite precision using pulsar timing observations. Some alternative theories of gravity predict tiny deviations from general relativity that would only become apparent in very strong gravitational fields. Neutron stars provide the ideal testing grounds for these alternative theories, as their gravitational fields approach the maximum possible strength without forming black holes. So far, all observations have consistently supported Einstein's theory, but continued, long-term studies of neutron star systems may eventually reveal new physics that lie beyond general relativity. The gravitational environment around neutron stars also affects the behavior of fundamental particles in ways that are impossible to study in terrestrial laboratories. The intense gravitational redshift can physically shift the energy levels of atoms and molecules, potentially affecting chemical reactions in the thin atmospheres of neutron stars. Quantum field theory in curved spacetime predicts that virtual particle pairs can be separated by these tidal forces, leading to particle creation near the neutron star. These exotic quantum effects in strong gravitational fields connect neutron star physics to some of the deepest questions in all of theoretical physics. How does quantum mechanics reconcile with general relativity? What happens to information when it falls into a strong gravitational field? can we understand the microscopic structure of space-time itself? Neutron stars provide natural laboratories where these profound questions might one day find their answers. The magnetic fields of neutron stars add yet another layer of complexity to their gravitational environments. Field strengths reaching 10 to the 15th power Gauss, a quadrillion times stronger than the strongest magnetic fields ever produced on Earth, interact with the curved spacetime in ways that are still being explored theoretically. The combination of extreme gravity and extreme magnetism creates unique plasma physics environments where both general relativity and quantum electrodynamics play crucial roles. As we prepare to delve deeper into the specific effects of neutron star gravity, from the conditions on their surfaces to the physics of their cores, it is important to appreciate the revolutionary nature of these objects. They represent the most extreme gravitational laboratories that are accessible to our observation, places where space-time curvature approaches its maximum possible value while still allowing matter to exist in a stable configuration. The transition from the broad framework of general relativity to the specific conditions at a neutron star's surface reveals how abstract mathematical concepts translate into observable, physical phenomena. Every single photon that escapes from a neutron star carries with it information about the curvature of spacetime. Every single pulse arrival time reflects the gravitational redshift. And every orbital measurement we take probes the warping of space and time around these cosmic laboratories. Understanding gravity at these extremes requires us to think far beyond our everyday experience and to embrace the strange, counterintuitive reality of curved spacetime, where time runs slow, distances contract, and the very fabric of reality bends under the influence of matter and energy compressed beyond all imagination. Standing on the surface of a neutron star would be an experience far beyond human comprehension, if such a thing were even theoretically possible. The gravitational field at the surface is so profoundly intense that it would crush any known material instantly. And yet, this extreme environment reveals some of the most fascinating physics in the entire universe. To understand what happens at a neutron star's surface, we must examine how gravity shapes every single aspect of this alien world, from the behavior of individual atoms to the structure of the star's outer layers. A typical neutron star measures only 10 to 12 kilometers in radius, roughly the size of a small city, yet it contains between 1.4 and 2.3 times the mass of our entire Sun. This incredible compression creates a surface gravity that is approximately 100 billion times stronger than what we experience on Earth. To put this in perspective, if you weigh 70 kilograms on Earth, you would weigh 7 trillion kilograms on a neutron star's surface. The gravitational acceleration reaches about 10 to the 11th power meters per second squared, compared to Earth's modest 9.8 meters per second squared. This extreme surface gravity has immediate and dramatic consequences for anything attempting to escape the neutron star's gravitational embrace. The escape velocity, the minimum speed needed for an object to break free from the gravitational pull, ranges from about 40 to 60% of the speed of light. This means that matter leaving a neutron star's surface must achieve velocities between 120,000 and 180,000 kilometers per second, speeds that challenge our understanding of physics and approach the cosmic speed limit. These escape velocities are so high that they affect the very nature of light itself. When photons are emitted from the neutron star's surface, they must climb out of this incredibly deep gravitational well, losing energy as they do. This energy loss manifests as the gravitational redshift, where the wavelength of the light becomes stretched as it escapes. X-rays emitted from the surface might arrive at Earth as ultraviolet light, while visible light would be stretched into infrared radiation. The magnitude of this gravitational redshift depends directly on the neutron star's mass and its radius, providing astronomers with a powerful diagnostic tool. By measuring how much the light from a neutron star has been redshifted, we can determine the strength of its surface gravity and, from that, constrain its physical properties. Recent observations by space-based X-ray telescopes have used this very technique to measure neutron star masses and radii with unprecedented precision. The surface itself presents a landscape utterly unlike anything in our solar system. The solid crust of a neutron star consists of atomic nuclei arranged in a crystalline lattice. But these are not ordinary atoms. The intense gravitational field compresses matter to such extreme densities that only the most neutron-rich nuclei can exist stably. Elements like iron-56, the most stable nucleus under normal conditions, actually become unstable in neutron star crusts. Here, nuclei with dozens of extra neutrons dominate. This crystalline crust is remarkably smooth, with any surface irregularities limited to just a few centimeters in height. The intense surface gravity simply prevents the formation of mountains or valleys any larger than this. Any deviation from a perfect sphere would create stresses that far exceed the breaking strength of even the strongest materials we can imagine. The surface is literally flattened by its own gravity to a degree of smoothness that surpasses our finest polished mirrors. Yet, despite this incredible smoothness, the neutron star's crust harbors incredible complexity. The outer layers consist of heavy nuclei embedded in a sea of electrons, with the nuclei arranged in what is called a body-centered cubic crystal structure. As you descend deeper into the crust, the neutron content of these nuclei increases dramatically. At depths of just a few hundred meters, the nuclei contain so many neutrons that they begin to approach the neutron drip line, the point where neutrons actually start to leak out of the atomic nuclei. The pressure at these depths reaches values that completely dwarf anything we can create on Earth. At only 1 kilometer below the surface, the pressure exceeds 10 to the 30th power pascals, which is billions of times greater than the pressure at the very center of the Earth. Under these conditions, the crystal lattice of nuclei becomes distorted, and exotic nuclear configurations may begin to form. Theoretical models predict the existence of nuclear pasta. This is a phase where nuclei, to minimize their energy, arrange themselves into rod-like, plate-like, or other non-spherical structures. This nuclear pasta phase represents one of the most unusual forms of matter in the universe. Computer simulations suggest that as the density increases, spherical nuclei first elongate into rod-shaped structures, which physicists call spaghetti. Then, they flatten into plates, which they call lasagna, before finally inverting into a foam-like structure with neutron-rich bubbles, which they call Swiss cheese. The names for these phases, cylindrical pasta, lasagna pasta, and Swiss cheese pasta, reflect their resemblance to familiar shapes, but their physical properties are anything but familiar. The gravitational field strength also varies noticeably, even across the neutron star's small surface. The difference in gravitational acceleration between the poles and the equator, which is due to the star's rapid rotation, can be significant for rapidly spinning neutron stars. Some neutron stars rotate hundreds of times every second, creating centrifugal forces that partially offset the gravitational pull at the equator. However, even the fastest spinning neutron stars cannot rotate quickly enough to significantly reduce their surface gravity, which remains many billions of times stronger than Earth's all across its surface. The interaction between the neutron star's intense gravitational field and its equally intense magnetic field creates additional complications at the surface. Neutron stars possess magnetic fields that can be trillions of times stronger than Earth's magnetic field. These magnetic fields, which were frozen into the neutron star during its formation, interact with the curved spacetime near the surface in ways that are still being studied theoretically. In the most highly magnetized neutron stars, known as magnetars, surface magnetic fields can reach 10 to the 15th power Gauss. At these field strengths, the magnetic energy density actually exceeds the energy density of matter itself, fundamentally altering the properties of atoms and molecules in the neutron star's atmosphere. The magnetic field becomes so strong that it can split photons into pairs of particles and antiparticles, creating a complex plasma environment just above the surface. The atmosphere of a neutron star, if one can even call it that, extends only a few centimeters above the solid surface. The intense gravitational field compresses any gaseous material into an incredibly thin layer with scale heights measured in centimeters, rather than the kilometers typical of planetary atmospheres. This thin atmosphere consists of the lightest elements available, typically hydrogen and helium, though even these are compressed to densities approaching that of liquid water. Within this compressed atmosphere, atoms behave in ways that would seem impossible under terrestrial conditions. The combination of extreme gravity and powerful magnetic fields can stretch atoms into needle-like shapes, with their electron orbitals distorted far from the familiar spherical or dumbbell forms. Spectral lines from these distorted atoms appear at wavelengths significantly different from their laboratory values, providing another signature of the extreme conditions at neutron star surfaces. The thermal properties of neutron star surfaces reflect their violent birth and their subsequent evolution. Newly formed neutron stars have surface temperatures of about 1 million degrees Celsius, hot enough to emit light primarily in the X-ray part of the spectrum. Over time, they cool by radiating this thermal energy away into space. Their surface temperatures drop to around 100,000 degrees Celsius after about 1 million years. This cooling process is not uniform across the entire surface. Hot spots, which are heated by the bombardment of charged particles accelerated in the neutron star's magnetosphere, can reach temperatures several times higher than the average surface temperature. These hotspots, typically located near the magnetic poles, are what create the lighthouse-like beams of radiation that we observe as pulsar signals. The gravitational redshift affects our observations of this thermal emission in important ways. The surface temperature that we calculate from our X-ray observations must be corrected for the gravitational redshift to determine the actual temperature at the neutron star's surface. This correction can be substantial, with the observed temperatures appearing 20 to 40% lower than the true surface values. Starquakes represent another fascinating consequence of neutron star surface gravity. As the neutron star cools and spins down over time, its shape must adjust to the changing rotational and magnetic stresses. The rigid crust occasionally fractures and rearranges itself to accommodate these changes, releasing enormous amounts of energy in events known as starquakes or neutron star glitches. These starquakes can release more energy than the largest earthquakes on our planet, despite involving fractures that are only millimeters in size. The extreme surface gravity ensures that even these tiny adjustments in the crust's structure involve tremendous forces. When a starquake occurs, it can suddenly change the neutron star's rotation rate, causing glitches in the pulsar's timing that astronomers can detect with high precision. The boundary between the neutron star's surface and its interior is not a sharp line, but rather a gradual transition from the solid crust to the liquid core. In the deepest layers of the crust, at densities approaching half of nuclear density, neutrons begin to drip out of the nuclei and form a neutron fluid that coexists with the crystalline lattice of neutron-rich nuclei. This neutron drip region marks the beginning of the transition to the neutron star's liquid interior. Surface effects also influence how we observe neutron star mergers and their gravitational wave signatures. When two neutron stars approach each other closely enough, their mutual gravitational attraction raises tides on each star's surface. These tidal bulges grow larger as the stars spiral inward, eventually disrupting the surface layers and creating the conditions for a kilonova explosion. The strength of the surface gravity determines how easily these tidal forces can disrupt the neutron star. Stars with stronger surface gravity are able to resist tidal disruption more effectively, while those with weaker surface gravity are more easily torn apart. By studying the gravitational wave signals from these neutron star mergers, astronomers can infer properties of the surface gravity and the internal structure of the merging stars. Recent observations have revealed that some neutron stars possess surface magnetic fields that are not uniformly distributed. Instead of simple dipole configurations, like Earth's magnetic field, these stars may have complex multipole field structures with strong variations across their surfaces. The interaction between these non-uniform magnetic fields and the curved spacetime near the surface creates intricate patterns of particle acceleration and radiation emission. The very concept of a neutron star surface also becomes somewhat ambiguous when we consider the effects of the surrounding magnetosphere. Charged particles that are trapped in the magnetic field can create an extended atmosphere, or corona, that stretches far above the solid surface. The boundary between the neutron star itself and its magnetospheric environment is thus not a sharp interface, but a gradual transition region where gravity, magnetic forces, and radiation pressure all play important roles. Understanding the properties of neutron star surfaces requires sophisticated computer models that must account for the complex interplay between gravity, magnetic fields, nuclear physics, and plasma physics. These models must solve Einstein's equations for the curved spacetime geometry while simultaneously calculating the behavior of matter and radiation in this extreme environment. The observational study of neutron star surfaces continues to advance with new space-based X-ray telescopes and improved ground-based instruments. Missions like NICER have provided unprecedented detailed observations of thermal emission from neutron star surfaces, allowing astronomers to map temperature variations and constrain the surface composition. Future missions promise even more detailed studies of these extreme gravitational environments. As we prepare to explore the interior regions of neutron stars, where gravity competes directly with quantum forces to determine the structure of matter itself, the surface serves as our observational window into these hidden realms. Every photon that escapes from a neutron star's surface carries information about the gravitational field, the magnetic environment, and the thermal conditions that exist in this most extreme of cosmic laboratories. The skin of a neutron star thus represents far more than simply the boundary between the star and empty space. It embodies the intersection of gravity, nuclear physics, and quantum mechanics, all operating under conditions that push our understanding of physics to its absolute limits, while remaining just accessible enough to our detailed observation that we can begin to unravel the mysteries of matter under extreme gravitational stress. Deep within a neutron star, an epic battle rages between two of nature's most fundamental forces. On one side stands gravity, relentlessly crushing matter toward infinite density with a strength that grows more powerful with each passing moment of collapse. On the other side stands quantum mechanics, specifically the Pauli exclusion principle, which creates a powerful outward pressure that refuses to allow identical particles to occupy the same quantum state. This cosmic struggle determines not only the very structure of neutron stars, but also provides us with a natural laboratory where quantum effects operate on astronomical scales. To understand this battle, we must first appreciate the extraordinary nature of neutron degeneracy pressure. In ordinary matter, atoms maintain their structure through electromagnetic forces that keep electrons in orbitals around their atomic nuclei. But in neutron stars, gravity has compressed matter far beyond the point where atoms can exist. Instead, the stellar interior consists primarily of neutrons, all packed together at densities that approach and even exceed that of an atomic nucleus. These neutrons, like all particles with half-integer spin, are fermions, which means they must obey the Pauli exclusion principle. This quantum mechanical rule states that no two identical fermions can occupy the same quantum state at the same time. In practical terms, this means that all the neutrons in a neutron star cannot just drop down to the lowest possible energy level as they would in a classical system. Instead, they are forced to fill progressively higher and higher energy levels, creating what physicists call a degenerate neutron gas. The pressure created by this quantum effect is truly remarkable. Unlike the thermal pressure in ordinary matter, which depends on temperature, degeneracy pressure depends only on the density of the particles. Even at temperatures near absolute zero, a degenerate neutron gas would maintain an enormous pressure, simply because of the quantum mechanical requirement that the neutrons must avoid each other in phase space. This pressure increases rapidly with density, following a relationship where the pressure grows as the density is raised to the 5/3 power. The strength of neutron degeneracy pressure in these stellar cores is almost beyond comprehension. In the central regions of a neutron star, this quantum pressure can reach values of 10 to the 35th power pascals. This is a pressure so enormous that it has no meaningful comparison in our everyday experience. To put this in perspective, this pressure exceeds the pressure at the center of our Sun by factors of billions, and it surpasses the strongest pressures we can create in our laboratory experiments by similar margins. This quantum pressure provides the only known mechanism capable of halting the gravitational collapse of a stellar core once nuclear fusion has ceased. When the core of a massive star begins its final, catastrophic collapse, gravity initially wins the battle decisively. The core shrinks from thousands of kilometers in diameter to just tens of kilometers in less than a second. But as the density approaches nuclear density, neutron degeneracy pressure begins to assert itself with rapidly increasing strength. The precise moment when degeneracy pressure halts, the collapse depends on the delicate balance between the strength of gravity and the stiffness of the equation of state, which relates pressure to density. If gravity is too strong, or if the neutron degeneracy pressure is insufficient, the collapse continues right past the neutron star stage and forms a black hole instead. The boundary between these two outcomes defines one of the most important thresholds in all of astrophysics. Current theoretical models suggest that neutron degeneracy pressure can support stellar masses up to approximately 2 to 3 solar masses, though the exact upper limit remains uncertain. This maximum mass, known as the Tolman-Oppenheimer-Volkoff limit, represents the point where gravity finally and definitively overwhelms quantum mechanics. Beyond this mass threshold, no known form of matter can resist the gravitational collapse, and the formation of a black hole becomes inevitable. The density gradient within a neutron star reveals how this quantum gravitational struggle plays out across the different regions of the stellar interior. Near the surface, densities remain below nuclear density, and matter exists in the form of neutron-rich atomic nuclei embedded in a sea of electrons. But as we move deeper into the star, the density increases dramatically, and the very nature of matter undergoes fundamental changes. At the neutron drip density, which is roughly half of nuclear density, neutrons begin to leak out of the atomic nuclei and exist as free particles. This marks the beginning of the regime where neutron degeneracy pressure becomes the dominant force. The free neutrons form a quantum fluid that coexists with the remaining neutron-rich nuclei, creating a complex, two-component system where both electromagnetic and strong nuclear forces play important roles. Deeper still, at densities approaching nuclear density, the distinction between individual nuclei disappears entirely. Matter transforms into a uniform fluid of neutrons, protons, and electrons, with the neutrons vastly outnumbering the other types of particles. In this regime, neutron degeneracy pressure provides the primary support against gravitational collapse, while the protons and electrons contribute smaller, but still significant pressure components. The quantum nature of this neutron fluid leads to several remarkable properties that have no analog in everyday matter. At the extreme densities found in neutron star cores, neutrons can form Cooper pairs and undergo a phase transition into a superfluid state. This neutron superfluid exhibits zero viscosity, meaning it can flow through the solid crust without any friction. This leads to complex dynamics that affect the neutron star's rotation and the evolution of its magnetic field. Theoretical calculations suggest that different regions of the neutron star's interior may undergo this superfluid transition at different temperatures and densities. The neutron superfluid transition might occur at temperatures around 10 to the 9th power Kelvin. This is far higher than any terrestrial superfluid, but it is still well below the initial temperature of a newly formed neutron star. As the star cools over millions of years, different layers may sequentially transition into this superfluid state. The presence of superfluidity has observable consequences for a neutron star's behavior. Pulsar glitches, those sudden, abrupt increases in the rotation rate of pulsars, are thought to be the result of the interaction between the superfluid neutron component and the normal matter in the crust. When the superfluid neutrons, which continue to rotate at their original rate, suddenly couple to the slowing down crust, they transfer angular momentum and cause the observed glitch. Protons in the neutron star core may also undergo a similar phase transition, forming superconducting Cooper pairs at temperatures around 10 to the 10th power Kelvin. This proton superconductivity would have dramatic effects on the neutron star's magnetic field evolution, as superconductors actively expel magnetic fields through the Meissner effect. The competition between this magnetic field expulsion and the relentless gravitational compression creates complex field configurations that are still being studied theoretically. The equation of state that describes how pressure relates to density in neutron star matter remains one of the most uncertain aspects of neutron star physics. Unlike ordinary matter, where we can measure these pressure-density relationships in laboratory experiments, neutron star matter exists only under conditions that cannot be reproduced on Earth. Our particle accelerators can create individual neutrons and study their interactions, but they cannot create the bulk, properties of neutron matter at nuclear density. This uncertainty in the equation of state has profound implications for our understanding of neutron star structure. A stiff equation of state, where pressure increases rapidly with density, produces larger neutron stars that can support higher maximum masses. A soft equation of state, where pressure increases more slowly, leads to more compact stars with lower maximum masses. Observations of neutron star masses and radii thus provide crucial constraints on the fundamental properties of matter at these extreme densities. Recent gravitational wave observations of merging neutron stars have begun to shed light on these equation of state uncertainties. When two neutron stars spiral into each other, they experience extreme tidal forces that deform their shapes. The amount of this deformation depends sensitively on the neutron star's internal pressure distribution, which in turn depends on the equation of state. By measuring these tidal effects in the gravitational wave signals, astronomers can constrain the stiffness of neutron matter. The quantum mechanical nature of neutron degeneracy pressure also affects how neutron stars respond to perturbations. Unlike classical fluids, degenerate neutron matter exhibits complex oscillation modes that depend on quantum statistical effects. These stellar oscillations, which might be triggered by events like starquakes or tidal interactions, can generate gravitational waves with characteristic frequencies that encode information about the neutron star's internal structure. Computer simulations of neutron star interiors must account for both the quantum mechanical behavior of degenerate matter and the strong gravitational fields described by general relativity. These calculations require sophisticated numerical techniques that solve the Einstein field equations while simultaneously tracking the quantum statistical properties of the neutron matter. The computational demands are enormous, requiring some of the world's most powerful supercomputers. The competition between gravity and quantum forces also determines the thermal evolution of neutron stars. Young neutron stars cool primarily through neutrino emission, as these weakly interacting particles can escape freely from the stellar interior. The rate of this neutrino emission depends on the quantum properties of the neutron matter, including the onset of superfluidity and the potential presence of exotic particles in the core. Different theoretical models of neutron matter predict vastly different cooling rates. Models that include exotic particles, like hyperons or quark matter, generally predict faster cooling, as these particles provide additional neutrino emission mechanisms. Models that include only nucleons, protons, and neutrons cool more slowly, as neutrino emission becomes suppressed at lower temperatures. Observations of neutron star temperatures at different ages thus provide another way to constrain the properties of ultra-dense matter. The quantum nature of neutron star matter also affects its response to magnetic fields. In terrestrial materials, magnetic fields interact primarily with electrons. But in neutron stars, the magnetic field must interact with the degenerate neutron matter itself. This leads to novel phenomena, like magnetic field-induced changes in the equation of state and the possibility of magnetically driven phase transitions in the stellar core. Some theoretical models suggest that extremely strong magnetic fields, like those found in magnetars, might actually alter the balance between gravity and quantum pressure. The magnetic energy density in these objects can become comparable to the matter energy density, potentially affecting the star's structure and stability. Understanding these magneto-hydrodynamic effects requires combining quantum statistical mechanics with magnetized general relativity. The study of neutron star oscillations provides another window into the quantum gravitational battle occurring in their cores. These oscillations, which are analogous to seismic waves in planets, propagate through the neutron star interior and carry information about the local pressure, density, and composition. The frequencies and damping rates of these modes depend sensitively on the quantum properties of the neutron matter. Future gravitational wave detectors may be sensitive enough to observe these stellar oscillation modes directly. Different theoretical models of neutron matter predict different oscillation spectra. So, gravitational wave asteroseismology could potentially distinguish between competing equations of state. This would provide an unprecedented probe of quantum mechanics operating under extreme gravitational conditions. The quantum mechanical uncertainty principle also plays a subtle but important role in neutron star physics. The zero-point motion of neutrons, which is required by quantum mechanics even at absolute zero temperature, contributes to the neutron pressure and affects the minimum possible radius of neutron stars. This quantum mechanical effect sets a fundamental lower limit on neutron star sizes that depends only on basic physical constants. As we probe deeper into neutron star cores, approaching densities that exceed nuclear density by factors of several, the quantum gravitational struggle becomes even more intense. The extreme conditions in these central regions may give rise to new phases of matter that exist nowhere else in the universe, representing the ultimate testing ground for our understanding of how quantum mechanics and gravity interact when both are pushed to their absolute limits. The victory of quantum degeneracy pressure over gravitational collapse in neutron stars represents one of the most dramatic demonstrations of quantum mechanics operating on cosmic scales. Yet, this victory is only temporary and conditional. It is dependent on the star's mass remaining below that critical threshold where gravity finally and inevitably wins. Understanding this cosmic battle between fundamental forces continues to drive both theoretical advances and observational discoveries, as we seek to unravel the deepest mysteries of matter, energy, and space-time under the most extreme conditions that nature can provide. At the very heart of a neutron star lies a realm so exotic that it challenges our most fundamental understanding of matter itself. Here, in a sphere that is perhaps just a few kilometers across, gravity has compressed matter to densities that exceed those found in atomic nuclei by factors of 5 to 10. These are conditions so extreme that they exist nowhere else in the observable universe, creating a natural laboratory where the most basic building blocks of reality are pushed beyond their normal limits. Nuclear density, the density of matter inside an atomic nucleus, is approximately 2.3 times 10 to the 14th power grams per cubic centimeter. This is already an almost incomprehensible number, roughly equivalent to compressing all the automobiles on Earth into a space the size of a sugar cube. Yet in the cores of neutron stars, densities can reach 5 to 10 times this value, creating conditions where the very concept of individual nucleons, protons and neutrons, begins to break down. To understand what happens under such extreme compression, we must first consider what we know about the fundamental structure of matter. Protons and neutrons, the particles that make up atomic nuclei, are not truly elementary particles. Instead, they are composite objects, themselves made up of more fundamental constituents called quarks, which are held together by the strong nuclear force, mediated by particles called gluons. Under normal conditions, quarks are permanently confined within nucleons and cannot exist as free particles. But the extreme gravitational compression in neutron star cores may be sufficient to overcome this quark confinement, leading to a phase transition where protons and neutrons dissolve into their constituent quarks. This hypothetical state of matter, known as quark matter or strange matter, would represent a fundamentally different phase of material existence, as alien to normal matter as plasma is to ordinary gas. The transition to quark matter, if it does occur, would likely happen gradually as the density increases toward the neutron star's center. Theoretical models suggest that this transition might begin at densities around 2 to 3 times nuclear density, though the exact threshold remains highly uncertain. The process would not be a sharp boundary, but rather a gradual crossover region where nucleons slowly lose their individual identity and merge into a soup of deconfined quarks and gluons. In this quark soup, the fundamental particles would behave according to a different set of rules than those governing normal. Nuclear matter. Instead of neutrons and protons interacting through nuclear forces, we would have up quarks, down quarks, and possibly strange quarks, all interacting through the strong force in its most fundamental form. The pressure support against gravitational collapse would come not from neutron degeneracy, but from quark degeneracy pressure, potentially creating a stiffer equation of state that could support higher maximum neutron star masses. The presence of strange quarks in neutron star cores opens up even more exotic possibilities. Strange quarks are heavier than the up and down quarks that make up normal matter. But at the extreme densities found in neutron star cores, it might become energetically favorable to convert some of the up and down quarks into strange quarks. This would create strange quark matter, a hypothetical form of matter that some theories suggest might be absolutely stable, even more stable than normal nuclear matter. If strange quark matter is indeed the true ground state of matter at high densities, then neutron stars might not be neutron stars at all, but rather strange stars composed primarily of strange quarks. These objects would have subtly different properties from neutron stars, including different mass-radius relationships and different cooling behaviors. Distinguishing between neutron stars and strange stars remains one of the major challenges in neutron star astronomy. Another exotic possibility in neutron star cores is the formation of hyperon matter. Hyperons are particles that are similar to neutrons and protons, but contain strange quarks. Under the extreme conditions in neutron star cores, it might become energetically favorable to convert some neutrons into hyperons, such as lambda particles, sigma particles, or Xi particles. These particles are highly unstable under normal conditions, but could be stabilized by the extreme densities and pressures in neutron star cores. The presence of hyperons would significantly soften the equation of state, which reduces the pressure supporting the star against gravitational collapse. This creates what theorists call the hyperon puzzle. If hyperons form easily in neutron star cores, they would make it very difficult to explain the existence of neutron stars with masses above 2 solar masses, which we have observed. Resolving this puzzle requires either that hyperons are somehow suppressed by other forces or that other exotic physics comes into play. Kaon and pion condensation represent yet another class of exotic phenomena that might occur in neutron star cores. These are states where certain types of meson particles, made up of quark-antiquark pairs, form macroscopic quantum condensates, similar to superconductivity or superfluidity. The formation of these condensates would alter the equation of state and could have observable consequences for the neutron star's cooling and the evolution of its magnetic field. The extreme gravitational fields in neutron star cores also raise the possibility that entirely new forms of matter might exist that have no terrestrial analogs. Some theoretical models suggest that color superconductivity, where quarks themselves form Cooper pairs similar to electrons in ordinary superconductors, might develop in dense quark matter. This would create a state where the strong force exhibits phenomena analogous to the Meissner effect in electromagnetic superconductors. Temperature plays a crucial role in determining which of these exotic phases might exist in neutron star cores. Young neutron stars have core temperatures of around 10 to the 10th power Kelvin, hot enough that these thermal effects could suppress some of the phase transitions. As the neutron star cools over millions of years, different exotic phases might appear sequentially, potentially creating layered structures with different types of matter at different depths within the core. The cooling process itself depends sensitively on the composition of the core. Different exotic particles provide different neutrino emission mechanisms, leading to characteristic cooling signatures that can be observed by our X-ray telescopes. Fast cooling typically indicates the presence of exotic particles that enhance neutrino emission, while slow cooling suggests a core composed primarily of nucleons. Recent observations of neutron star cooling curves have provided important constraints on their core composition. Some neutron stars appear to cool faster than predicted by models containing only nucleons, suggesting the presence of exotic particles or phase transitions in their cores. Other neutron stars cool more slowly, indicating either efficient superfluidity, which suppresses neutrino emission, or cores that remain in the nucleonic phase. The magnetic field evolution of neutron stars also depends on their core composition. Superconducting or superfluid phases in the core would expel magnetic flux, forcing the field lines to concentrate in the normal matter regions. This could lead to complex field configurations and a time-dependent evolution of the magnetic field that might be observable through changes in a pulsar's spin-down rate or its emission properties. Theoretical studies of neutron star core composition require sophisticated techniques from quantum chromodynamics, or QCD, the theory of the strong nuclear force. However, QCD calculations at high density and low temperature remain extremely challenging, even with the most powerful supercomputers currently available. Most current models must rely on simplified approximations or phenomenological approaches that may not capture the full complexity of this ultra-dense matter. Lattice QCD. Calculations, which discretize spacetime to make the equations tractable for computers, have made significant progress in recent years, but still cannot fully reach the densities and temperatures that are relevant for neutron star cores. Alternative approaches, like effective field theories and functional renormalization group methods, provide complementary insights, but come with their own limitations and uncertainties. Experimental constraints on the properties of ultra-dense matter come primarily from heavy ion collision experiments at facilities like the Relativistic Heavy Ion Collider, or RHIC, and the Large Hadron Collider, or LHC. These experiments create hot, dense nuclear matter for brief moments, allowing physicists to study the properties of quark-gluon plasma and the transition between different phases of matter. However, the conditions in these experiments, very hot, less dense, differ significantly from those in neutron star cores, very cold, much denser, making any direct extrapolation difficult. The study of neutron star mergers has opened a new window into core physics. When two neutron stars collide, they probe the equation of state at the highest densities reachable before the remnant collapses into a black hole. The gravitational wave signals from these mergers encode information about how matter behaves under this extreme tidal stress, providing constraints on whether the cores are composed of nucleons, quarks, or more exotic forms of matter. The tidal deformability, measured in these gravitational wave observations, provides particularly strong constraints on the equation of state at high densities. Stiffer equations of state, which are characteristic of nucleonic matter, produce less deformable neutron stars. Softer equations of state, which might be expected for quark matter or hyperon matter, lead to more easily deformed stars. Current observations tend to favor an intermediate stiffness, suggesting either nucleonic matter with strong repulsive interactions or perhaps a mixture of nucleonic and exotic phases. Future gravitational wave observations promise even tighter constraints on core composition. Third-generation detectors, like the Einstein telescope and the Cosmic Explorer, will be sensitive enough to detect neutron star oscillations and potentially observe phase transitions in real time, as the stars are compressed beyond critical densities during the merger. The maximum mass of neutron stars provides another crucial constraint on core physics. Different theoretical models predict different maximum masses, depending on the assumed composition and equation of state. The observation of neutron stars with masses around 2 solar masses already rules out many of the soft equations of state and constrains the density at which exotic phases can appear. Recent discoveries of neutron stars with masses approaching 2.5 solar masses, if they are confirmed, would place even stronger constraints on core composition. Such massive neutron stars would require very stiff equations of state, possibly ruling out hyperon matter entirely and favoring either nucleonic matter with very strong repulsive forces, or a transition to self-bound quark matter at high densities. The possibility that neutron star cores contain absolutely stable, strange quark matter raises profound questions about the ultimate fate of matter in the universe. If strange matter is indeed more stable than nuclear matter, then neutron stars might, over immense timescales, gradually convert into strange stars through quantum tunneling processes, though this conversion would likely take much longer than the current age of the universe. Some theorists have speculated about even more exotic possibilities within neutron stars, including the formation of boson stars, crystalline quark phases, or even microscopic black holes that could exist stably within the neutron star's interior. While these ideas remain highly speculative, they illustrate the vast range of possibilities when matter is compressed to densities that approach the fundamental scales of particle physics. The study of neutron star cores also connects to broader questions in fundamental physics, including the nature of confinement in quantum chromodynamics, the possibility of new phases of matter at high density, and the relationship between gravity and the strong nuclear force. Neutron stars thus serve as cosmic laboratories for testing our most basic theories about the structure of matter and the fundamental forces of nature. As observational techniques continue to improve and our theoretical calculations become more sophisticated, our understanding of neutron star cores will undoubtedly evolve. Each new discovery, whether it comes from gravitational wave detectors, X-ray telescopes, or particle physics experiments, adds another piece to the complex puzzle of what happens when gravity compresses matter beyond the limits of all terrestrial experience. The cores of neutron stars represent the ultimate frontier where astrophysics meets particle physics, where general relativity encounters quantum chromodynamics, and where our understanding of matter under extreme conditions is pushed to its absolute limits. In these alien realms, hidden deep within collapsed stellar cores, nature may have created forms of matter so exotic that they challenge our most fundamental assumptions about the building blocks of reality itself. Neutron stars present one of the greatest observational challenges in all of astronomy. These objects exist in environments so extreme that no spacecraft could possibly survive within millions of kilometers of their surfaces, and no laboratory on Earth can ever recreate the conditions found in their interiors. Yet, remarkably, astronomers have developed ingenious methods to probe the gravitational fields of these distant objects with extraordinary precision. They use techniques that transform the neutron stars themselves into cosmic measuring instruments. The story of neutron star observation begins with one of the most serendipitous discoveries in modern astronomy. In 1967, Graduate student named Jocelyn Bell Burnell was analyzing data from a radio telescope when she noticed strange, regular pulses coming from a particular region of the sky. These pulses arrived with such perfect, clockwork precision that the research team initially wondered if they might be signals from an extraterrestrial civilization. They even gave the source the tongue-in-cheek designation LGM-1 for Little Green Men 1. The true nature of these signals soon became clear. They were observing a rapidly rotating neutron star. Its powerful magnetic field was accelerating charged particles to enormous energies, creating beams of radiation that swept across space like a cosmic lighthouse. Each pulse represented one single rotation of the neutron star, and the incredible regularity of these pulses immediately suggested their potential as precision clocks for studying gravitational effects. Pulsar timing represents perhaps the most precise measurement technique in all of astronomy. The best-known pulsars maintain a timing stability that rivals our best atomic clocks, with their pulse arrival times predictable to microsecond accuracy over periods of years or even decades. This extraordinary precision allows astronomers to detect minuscule variations in the pulsar signals, variations that reveal information about the neutron star's gravitational environment and its internal structure. The basic principle behind pulsar timing is elegantly simple. Radio telescopes on Earth record the arrival times of individual pulses from a pulsar, building up a detailed long-term record of the neutron star's rotation. Any deviation from perfectly regular timing can reveal physical processes that are affecting the neutron star or its environment. Changes in the rotation rate might indicate internal adjustments in the star's structure, while tiny variations in the pulse arrival times could signal the presence of gravitational waves passing through our solar system. Gravitational redshift provides one of the most direct ways to measure the strength of a neutron star's surface gravity. As photons climb out of the deep gravitational well surrounding a neutron star, they lose energy and become redshifted to longer wavelengths. By comparing the observed frequencies of spectral lines from neutron star atmospheres with their known laboratory values, astronomers can determine the gravitational redshift and, from that, constrain the neutron star's mass and radius. This technique requires extremely high-resolution spectroscopy to detect the relatively small wavelength shifts involved. Typical gravitational redshifts from neutron stars range from about 10 to 40%, depending on the star's compactness. While these shifts are large compared to those from ordinary stars, they still require sophisticated instrumentation to measure accurately, particularly given the faintness of most neutron stars in optical and ultraviolet light. The neutron star, Interior Composition Explorer, or NICER, which is mounted on the International Space Station, has revolutionized our ability to study neutron star surfaces through X-ray timing and spectroscopy. This remarkable instrument can measure X-ray pulse profiles with unprecedented precision. This allows astronomers to map temperature variations across neutron star surfaces and to constrain their masses and radii through detailed modeling of the observed light curves. NICER exploits the phenomenon of gravitational light bending around neutron stars. The intense gravitational field curves space-time so severely that light rays follow bent paths. This allows observers to see emission from regions of the neutron star surface that would normally be hidden behind its own horizon. As hot spots on the surface rotate in and out of view, the gravitational lensing effect modulates the observed X-ray flux in characteristic ways that depend directly on the neutron star's mass and radius. The mathematical modeling required to extract mass and radius measurements from NICER observations involves solving the equations of general relativity in the strong field regime around these stars. Computer codes must account for the curved spacetime geometry, the propagation of photons through this geometry, and the emission properties of matter in the neutron star's extreme magnetic and gravitational environment. The precision of these measurements is now approaching the level needed to distinguish between different theoretical models of ultra-dense matter. Binary pulsar systems provide even more powerful laboratories for studying neutron star gravity. When two neutron stars orbit each other, they create a dynamic gravitational environment where the spacetime curvature changes continuously as the stars move through their orbits. The precision timing of the pulsar signals allows astronomers to track these orbital changes with extraordinary accuracy, revealing the effects of general relativity in the strong field regime. The Hulse-Taylor binary pulsar, discovered in 1974, provided the first compelling evidence for the emission of gravitational waves. Imagine two incredibly dense objects, neutron stars, locked in a cosmic dance, spinning around one another. As these two neutron stars circle each other in their orbit, they continuously send out ripples through the fabric of space and time itself. These ripples are known as gravitational waves. These waves are not just theoretical. They actively carry energy away from the orbiting system. This loss of orbital energy has a direct consequence. The orbit of the two stars begins to get smaller, or shrink. This shrinking doesn't happen randomly. It occurs at a rate that scientists can calculate and predict with extreme accuracy. This phenomenon provided a perfect test for Albert Einstein's groundbreaking theory of general relativity. According to Einstein's equations, there was a specific predicted rate for this orbital decay. When astronomers observed this system, they found that the actual measured decay of the orbit matched the mathematical predictions from the theory. The match was astonishingly close, accurate to within a tiny fraction of 1%. This remarkable confirmation of Einstein's theory was so significant that it earned the discoverers, Russell Hulse and Joseph Taylor, the Nobel Prize in Physics. Since that initial discovery, scientists have found other binary pulsar systems, pairs of pulsars orbiting each other. These newer discoveries have allowed for even stricter, more demanding tests of general relativity, and they have also helped us place limits or constraints on the physical properties of the neutron stars themselves. A particularly incredible example is the double pulsar system designated PSRJ 0737-3039A. This unique system features two separate active pulsars, both sending out beams of radiation as they orbit one another at an incredible speed, completing a full orbit in just 2.4 hours. This specific system provides a treasure trove of data, allowing astronomers to study the intricate gravitational effects from both of the neutron stars at the same time. This simultaneous observation provides multiple independent ways to measure their masses and allows for testing general relativity with a level of precision that was previously unheard of. The orbital dynamics, that is, the specific way these binary pulsars move and interact, hold encoded information. This information tells us about the masses of the neutron stars, revealed through the powerful gravitational effects they exert on each other. Johannes Kepler's laws of planetary motion, when updated and modified to account for the rules of general relativity, provide a link. They connect the orbital period, how long an orbit takes, the eccentricity, how stretched out the orbit is, and other orbital parameters directly to the masses of the individual stars in the system. By carefully measuring several different relativistic effects, all within the same binary system, astronomers can effectively solve a complex equation. This solution reveals the masses of both neutron stars independently of each other. This is crucial because it provides strict constraints on the absolute maximum mass that a neutron star can possibly reach before it collapses. Some of these binary pulsar systems demonstrate a fascinating effect known as orbital precession. This means that their elliptical or oval-shaped orbit does not stay fixed in one position. Instead, the entire orbit slowly rotates in space. This rotation is a direct consequence of the general relativistic effects caused by the warped spacetime. The specific rate of this precession, how fast the orbit turns, depends on the total combined mass of the system. This gives scientists yet another independent tool to constrain the masses of the neutron stars. The precision we can achieve with pulsar timing is astonishing. Astronomers are able to measure precession rates of just a few degrees over the course of an entire year. This is a motion far, far smaller and more subtle than the relativistic precession observed in Mercury's orbit as it moves around our Sun. Gravitational time dilation within these binary systems creates even more observable effects. The intensely strong gravitational field of each neutron star actually causes time to run slower in its immediate vicinity. This slowing of time directly affects the observed pulse frequencies coming from the pulsars. As the pulsars travel along their elliptical paths, they move into regions of stronger and weaker gravity. This varying gravitational time dilation creates periodic, predictable variations in their pulse rates. These tiny variations can be measured with high-precision timing observations over time. A new era in studying neutron star gravity began with the discovery of gravitational waves by the Laser Interferometer Gravitational Wave Observatory, commonly known as LIGO, and its European partner, Virgo. This achievement opened an entirely new window onto the universe, allowing us to listen to cosmic events rather than just see them. When two neutron stars spiral closer and closer into each other and finally merge, they generate some of the most powerful gravitational wave signals that our current instruments are capable of detecting. These incredible cosmic collisions provide unique information about the properties of neutron stars, information that simply cannot be gathered using any other observational technique. The gravitational wave signal coming from a neutron star merger is packed with detailed information. It tells us about the star's internal structure, revealed through what are known as tidal effects. As the two neutron stars get closer during their final frantic spiral, their powerful mutual gravitational attraction raises tides on each star's surface. This is similar to how our moon raises tides on Earth, but vastly more extreme. These forces deform the stars, stretching them from perfect spheres into elongated teardrop-like shapes. The exact amount of this deformation, how much they stretch, depends directly on the internal pressure distribution of the neutron stars. This, in turn, is dictated by the equation of state, a fundamental physical rule that describes how ultra-dense matter behaves. Measurements of this tidal deformability, extracted from gravitational wave observations, have given us some of the strongest constraints ever obtained on the properties of matter at nuclear density, and even beyond. The very first neutron-star merger that was detected by LIGO, an event which has been given the designation GW170817, provided crucial data. This event tended to favor equations of state that had an intermediate level of stiffness. This finding effectively ruled out two extreme possibilities. It ruled out the very soft models, which would imply neutron stars are highly deformable, and it also ruled out the very stiff models, which would make them behave almost like rigid, unchangeable objects. The electromagnetic counterpart to this gravitational wave event, that is, the light and radiation observed by traditional telescopes across the entire spectrum, from gamma rays all the way to radio waves, provided even more insights into neutron star physics. The visible light and near-infrared emission that followed the merger was powered by the radioactive decay of heavy elements. This light confirmed that these neutron star collisions are, in fact, major factories for what is called rapid neutron capture nucleosynthesis. This is the process that creates many of the heaviest elements in the universe, such as gold, platinum, and uranium. Future gravitational wave detectors promise to deliver even more precise measurements of neutron star properties. Third-generation instruments, with names like the Einstein Telescope and Cosmic Explorer, will be significantly more sensitive. They will be sensitive enough to detect neutron star mergers happening throughout most of the observable universe. This will provide enormous statistical samples, allowing us to study the entire neutron star population in great detail. These advanced detectors might also be sensitive enough to observe the individual oscillation modes of a neutron star, the way it rings like a bell. This would open up an entirely new field of study: gravitational wave asteroseismology. Measuring a neutron star's moment of inertia offers another window into its internal structure. The moment of inertia is a physical property that describes how mass is distributed within the star. Stars with more mass concentrated toward their center will have smaller moments of inertia. For neutron stars, this property is highly sensitive to the equation of state, especially in the core regions. These are the regions where exotic, non-standard phases of matter might exist. Several binary pulsar systems have shown evidence for an effect called geodetic precession. This is a phenomenon where the neutron star's spin axis, the imaginary line it rotates around, slowly precesses, or wobbles, due to the curved spacetime within the binary orbit. The speed, or rate, of this precession depends on the neutron star's moment of inertia. This provides a method to constrain that internal mass distribution. However, accurately measuring geodetic precession is incredibly difficult. It requires extremely long baseline observations, often spanning many years, and meticulous analysis to separate this subtle effect from other potential influences. The study of glitches in neutron stars also gives us insights into their internal structure and dynamics. Glitches are sudden, abrupt increases in a pulsar's rotation rate. They unexpectedly speed up. These events are thought to be the result of interactions between two different components inside the star: the superfluid neutron component in the core, which can rotate without friction, and the normal matter that makes up the star's crust. The size of a glitch and the frequency with which glitches occur seem to depend on the total amount of superfluid present inside the star and the strength of the coupling, or stickiness, between these different components. This provides valuable constraints on the physics of the neutron star's interior. Very large glitches, which have been observed in pulsars like the famous Veil pulsar, strongly suggest the presence of a substantial superfluid component deep within neutron star cores. The behavior after a glitch is also informative. This is known as the post-glitch recovery, where the pulsar's rotation gradually slows down, returning toward its pre-glitch rate. This recovery process tells us about the viscous coupling, or friction, between the superfluid and normal matter components. Different theoretical models predict different recovery timescales, allowing these observations to constrain the microphysical properties of neutron star matter. X-ray observations of the thermal emission, the heat radiating, from neutron stars provide yet another probe of their internal structure and composition. Young neutron stars cool down primarily by emitting neutrinos from their cores. The rate at which they cool is extremely sensitive to the composition and any phase transitions that might be occurring in the interior. If different exotic particles exist in the core, they provide different mechanisms for neutrino emission. This leads to characteristic cooling signatures that can be observed by X-ray telescopes. The observation of both fast-cooling neutron stars and slow-cooling neutron stars points to a diversity in what their cores are made of. Fast-cooling stars, which appear dimmer than expected for their age, typically indicate that there is enhanced neutrino emission. This could be caused by the presence of exotic particles like hyperons or even quark matter. On the other hand, slow-cooling neutron stars, which remain bright for longer than standard models predict, might be the result of superfluidity. In this case, the superfluid state actually suppresses the neutrino emission processes, acting like a blanket. Measurements of neutron star magnetic fields provide additional constraints on their structure and evolution. The strength of the magnetic field can be estimated from the pulsar's spin-down rate, the rate at which its rotation is slowing down. This calculation assumes that the energy loss is dominated by magnetic dipole radiation. For magnetars, which are a special class of neutron stars with incredibly powerful magnetic fields, X-ray observations of features called cyclotron lines allow for direct measurements of the magnetic field strengths at their surface. These measurements have reached staggering figures as high as 10 to the 15th power Gauss. The long-term evolution of these magnetic fields, how they change over millions of years, depends on the electrical conductivity of the star's interior. This, in turn, depends on the composition and phase structure of the core. For example, superconducting cores would exhibit complex behaviors like flux expulsion and different patterns of field decay. Normal conducting cores would show different evolutionary patterns entirely. Therefore, observing the magnetic field evolution across large populations of pulsars gives us indirect probes of the physics deep inside them. Radio polarization measurements of the signals from pulsars reveal information about the geometry of the magnetic field and the plasma environment immediately surrounding the neutron stars. A property called the rotation measure quantifies how much the polarization angle of the radio waves rotates as they travel through the star's magnetosphere. This rotation depends on both the magnetic field strength and the density of free electrons in the plasma. Observing changes in this rotation measure over time can indicate that the magnetic field configurations are evolving or that the plasma conditions around the star are varying. Recent advances in a technique called very long baseline interferometry have allowed astronomers to measure the proper motions and distances of nearby pulsars with extraordinary precision. These astrometric measurements, when combined with the pulsar timing data, provide independent constraints on the masses of neutron stars. They also enable powerful tests of gravitational theories in the strong field regime, where gravity is at its most extreme. Ultimately, the combination of multiple observational techniques provides the most powerful approach to understanding neutron star gravity and their internal physics. By bringing together data from pulsar timing, X-ray observations, gravitational wave detections, and the electromagnetic follow-up observations of events, astronomers can construct comprehensive pictures of individual neutron star systems. This allows them to constrain the fundamental properties of ultra-dense matter. As our observational capabilities continue to advance, the precision of these neutron star measurements is steadily improving. Next-generation radio telescopes, such as the Square Kilometre Array, will enable pulsar timing with sensitivity that was previously unimaginable. At the same time, improved X-ray missions will provide more detailed spectroscopic and timing observations of these objects. The synergy, or combined power, between all of these different observational approaches holds the promise of unlocking the remaining mysteries of neutron star physics. It will provide new insights into the behavior of matter under the most extreme gravitational conditions found anywhere in the universe. In the world of theoretical astrophysics, some of the most powerful tools for understanding neutron stars are not telescopes or detectors at all. Instead, they are supercomputers, machines capable of performing trillions of calculations every single second. These computational giants allow scientists to create virtual neutron stars inside a computer. These simulations are complete with their extreme gravitational fields, their exotic phases of matter, and their complex, evolving dynamics. Through these numerical simulations, researchers can explore scenarios that are impossible to observe directly, and they can test their theoretical predictions against the growing wealth of observational data. The challenge of simulating neutron star gravity begins with Einstein's field equations. These equations are the fundamental mathematical description of how matter and energy curve spacetime. Written in the complex language of differential geometry, these equations relate the curvature of spacetime at any given point to the local distribution of mass, energy, momentum, and stress. For neutron stars, where the gravitational fields are approaching their maximum possible strength, these equations must be solved with extraordinary precision to capture the physics accurately. Numerical relativity is the field of study devoted to solving Einstein's equations on computers. This field has undergone a revolution in recent decades. Early attempts to simulate systems with strong gravity often failed. They were plagued by numerical instabilities, where tiny computational errors would grow exponentially, ruining the calculation. However, breakthrough developments in the 1990s and 2000s led to stable mathematical formulations. These new methods could evolve neutron star spacetimes for the long periods needed to study their behavior properly. The basic approach involves a process called discretization. Spacetime is broken down into a three-dimensional grid of points, and the evolution through time is calculated one small step at a time. At each individual grid point, the computer stores values that represent the metric tensor, a mathematical object that describes the local geometry of spacetime. It also stores matter variables such as density, pressure, and velocity. The Einstein field equations are then approximated as finite difference equations, which relate the values at one grid point to the values at its neighboring grid points. Creating accurate simulations requires extremely careful attention to the equation of state. This is the physical relationship between pressure, density, temperature, and composition that determines how matter behaves under these extreme conditions. Unlike simulations of ordinary stars, where the equation of state is well understood, neutron star simulations must grapple with fundamental uncertainties. We simply do not know for sure how matter behaves at nuclear density and beyond. Different theoretical models of this ultra-dense matter lead to dramatically different predictions for a neutron star's structure and dynamics. For example, a stiff equation of state, one where pressure increases very rapidly with density, will produce larger neutron stars. These stars are more resistant to gravitational collapse. A soft equation of state, in contrast, leads to more compact stars, which have stronger surface gravity and different oscillation properties. Therefore, running simulations using these different equations of state serves as a powerful test of our understanding of fundamental physics. The computational demands for running these neutron star simulations are staggering. A typical three-dimensional simulation might use computational grids that contain millions or even billions of individual grid points. With each of those points requiring storage for dozens of different variables to describe the local state of matter and spacetime, the evolution equations must be solved thousands of times just to simulate 1 second of real time. This often requires weeks or even months of continuous computation on the world's most powerful supercomputers. One of the most crucial applications of numerical relativity is simulating neutron star mergers. These are the violent collisions that produce some of the strongest gravitational wave signals detectable by LIGO and Virgo. These simulations must accurately capture the complex interplay between many different branches of physics simultaneously: general relativity for gravity, fluid dynamics for the matter flow, magnetic fields, and nuclear physics. All of this happens as two neutron stars spiral into each other at velocities approaching the speed of light. The merger process itself unfolds over several distinct phases, and each phase presents its own unique computational challenges. During the inspiral phase, which can last for many orbital periods, the neutron stars remain largely intact. During this time, the emission of gravitational waves slowly drains energy from the orbit, pulling them closer. This phase requires long-duration simulations with very high accuracy to correctly predict the gravitational wave frequency evolution that our detectors observe. As the neutron stars approach their final plunge, tidal forces begin to deform their shapes significantly. The stars develop pronounced tidal bulges. These bulges grow larger as they spiral inward, and they eventually disrupt the surfaces of the stars, ejecting hot material into the surrounding space. Capturing this disruption process accurately requires extremely high resolution right near the stellar surfaces, pushing the available computational resources to their absolute limits. The actual merger, the moment when the two neutron star cores finally touch, releases an enormous amount of energy in just a fraction of a second. Temperatures inside the collision soar to tens of billions of degrees. Pressures exceed those found in the core of even the most massive stars. Matter is compressed to densities several times that of a normal atomic nucleus. This violent collision generates powerful shockwaves that propagate through the merged object, potentially triggering phase transitions to new, exotic forms of matter. Simulating the post-merger evolution, what happens after the collision, requires addressing even more complex physics. The remnant object, the thing left behind, might form a single massive neutron star, or it might collapse directly into a black hole. In either case, it undergoes violent oscillations, which generate gravitational waves at very high frequencies, several thousand hertz. These high-frequency oscillations contain information about the equation of state, and they could potentially be detected by future gravitational wave detectors. The evolution of the magnetic field during a merger presents another major computational challenge. Neutron stars possess magnetic fields that are trillions of times stronger than Earth's field. During the merger process, these fields become twisted, tangled, and amplified. The resulting magnetohydrodynamic turbulence can drive powerful jets of material away from the merger at nearly the speed of light. This process is the leading explanation for the short-duration gamma-ray bursts that are associated with some neutron star mergers. Simulating these magnetic fields within numerical relativity requires solving the equations of magnetohydrodynamics at the same time as Einstein's field equations. This involves tracking both the motion of the matter and the evolution of the magnetic field, all while ensuring that the field remains properly coupled to the conducting plasma. The computational cost for this increases significantly, as new magnetic field variables must be stored and evolved at every single grid point. Nuclear physics adds yet another layer of complexity to these simulations. As matter is compressed to extreme densities during the merger, it may undergo phase transitions. It might change into quark matter, hyperon matter, or other exotic phases. Each of these phases has different thermodynamic properties and contributes differently to the pressure that supports the star against gravitational collapse. Simulations must include realistic treatments of these phase transitions and their effects on the stellar structure. The synthesis of heavy elements during neutron star mergers, the rapid neutron capture process that creates elements like gold and platinum, requires detailed nuclear reaction networks. These networks involve tracking thousands of different isotopes. Simulations must track the abundances of all these isotopes as they are created, as they decay, and as they interact with each other in the extreme conditions following a merger. This nucleosynthesis is what determines the composition and properties of the material that is ejected from the merger site. Recent advances in computational techniques have enabled increasingly sophisticated neutron star simulations. A method called adaptive mesh refinement allows simulations to automatically increase their resolution in specific regions where high accuracy is needed, while using coarser grids elsewhere. This dramatically improves computational efficiency. Multiple coordinate systems can be used simultaneously to better handle the extreme gravitational fields near the surfaces of the neutron stars. Spectral methods, which represent functions as sums of smooth basis functions rather than discrete grid values, can achieve much higher accuracy than traditional finite difference schemes. These methods are particularly useful for simulating the long-term evolution of isolated neutron stars, where maintaining high accuracy over many rotation periods is essential for studying phenomena like magnetic field decay or thermal evolution. The validation of these numerical simulations is a critical step. It requires careful comparison with analytical solutions in simplified test cases. It also requires convergence testing to ensure that the results of the simulation become independent of the grid resolution used. Mock data challenges are also performed. In these challenges, simulated gravitational wave signals are analyzed using the exact same techniques that are applied to real detector data. This helps to verify that the simulations are accurately capturing the physics that is relevant for gravitational wave astronomy. Simulations have revealed many surprising aspects of neutron star physics that were not anticipated from analytical calculations alone. For example, the discovery that neutron star mergers can produce stable, massive remnants that survive for seconds or even longer before collapsing into black holes was a major surprise. This discovery required simulations to uncover. These hypermassive neutron stars are supported temporarily by their rapid rotation and by thermal pressure before they eventually succumb to gravitational collapse. The amount of material that gets ejected during neutron star mergers is crucial for understanding the synthesis of heavy elements and the electromagnetic counterparts to gravitational wave events. This amount depends very sensitively on the equation of state and can only be predicted accurately through detailed simulations. Different equations of state predict vastly different ejected masses, ranging from less than 1% to several percent of a solar mass. This has important implications for the chemical evolution of entire galaxies. Simulations have also revealed the complex dynamics of magnetic field amplification during mergers. The differential rotation and turbulence generated during the collision can amplify magnetic fields by factors of hundreds or even thousands. This can create field strengths that approach equipartition with the kinetic energy of the fluid motion. These amplified fields can, in turn, drive the powerful outflows that may be responsible for powering short gamma-ray bursts. The gravitational wave signals from neutron star mergers encode detailed information about the underlying physics. However, extracting this information requires accurate theoretical templates, which must be based on these numerical simulations. Researchers build template banks that contain hundreds of thousands of simulated waveforms. These banks allow gravitational wave detectors to identify merger signals in the noisy data and to measure their properties with high precision. Each new simulation that is run adds to this template bank and improves our ability to extract science from gravitational wave observations. Future developments in numerical relativity will likely focus on including even more realistic physics into neutron star simulations. Neutrino transport, for instance, plays an important role in the cooling and composition evolution of the merger remnants. This requires sophisticated radiation transport calculations that are computationally expensive, but they are becoming feasible with advancing computer power. The inclusion of weak interaction processes, such as beta decay and electron capture, affects the composition and thermal evolution of neutron star material during and after the merger. These processes determine the final neutron-to-proton ratio in the ejected material, and therefore influence the nucleosynthesis yields and the electromagnetic signatures of the kilonovae. Quantum effects, while typically negligible in classical astrophysical simulations, might become important in the extreme conditions near neutron star mergers. Quantum corrections to the equation of state, the formation of exotic quantum phases, and the behavior of matter in ultra-strong magnetic fields all represent frontier areas where simulations are just beginning to incorporate quantum mechanical effects. The development of what is known as exascale computing is set to completely revolutionize the field of neutron star simulations. These future machines will be capable of performing more than 10 to the 18th power calculations every single second. This represents an unprecedented level of computational power. It will enable simulations with much higher resolution, longer evolution times, and more complete physics than has ever been possible before. Machine learning techniques are also beginning to be applied to neutron star simulations. They are used both to accelerate the calculations and to extract hidden patterns from the large simulation datasets. Neural networks can be trained to approximate expensive calculations, like equation of state evaluations or nuclear reaction rates. This could potentially speed up simulations by orders of magnitude while still maintaining high accuracy. The ultimate goal of all neutron star simulations is to create a complete theoretical framework that can predict all the observable properties of these objects, starting from first principles. This requires bridging the gap between quantum chromodynamics, which governs the behavior of quarks and gluons at the smallest scales, and general relativity, which describes gravity and spacetime curvature at the largest scales. While this goal remains incredibly challenging, each advance in simulation capabilities brings us closer to a unified understanding of matter under these extreme conditions. Simulations also serve as virtual laboratories for testing ideas about neutron star physics that cannot be explored through observations alone. Questions about the maximum mass of neutron stars, the possibility of phase transitions in their cores, and the relationship between different observational signatures can all be addressed through carefully designed simulation studies. The synergy between simulations and observations has become one of the most powerful tools in modern neutron star astrophysics. Simulations guide the interpretation of observational data, while observations provide the crucial tests of the simulation's predictions. This feedback loop between theory and observation mediated by ever more sophisticated computer simulations, continues to drive our understanding of gravity and matter in their most extreme manifestations. As we stand on the threshold of even more advanced gravitational wave detectors and more sensitive electromagnetic telescopes, the role of numerical simulations in neutron star science will only grow in importance. These computational laboratories provide our best hope for understanding the fundamental physics operating in neutron star cores. They are key to unlocking the secrets of matter that has been compressed beyond the limits of all terrestrial experience. In the cosmic hierarchy of dense objects, neutron stars occupy a precarious position. They exist on the edge between ordinary matter and the ultimate gravitational abyss of black holes. There exists a critical threshold, a maximum mass. Beyond this limit, not even the quantum degeneracy pressure of neutrons can resist the relentless, crushing pull of gravity. When this limit is exceeded, the neutron star faces inevitable collapse into a black hole. This event marks one of the most dramatic phase transitions in the entire universe and represents gravity's final victory over all other forces of nature. The theoretical foundation for this mass limit was first laid in the 1930s by J. Robert Oppenheimer, Richard Tolman, and George Volkoff. They extended earlier work that had been done on white dwarf stars into the new realm of neutron degeneracy. Their calculations revealed a crucial difference. Unlike white dwarf stars, which can exist in a stable equilibrium at any mass below the Chandrasekhar limit, neutron stars face a more complex situation. Their maximum supportable mass depends critically on the properties of matter at nuclear density and even higher densities. The Tolman-Oppenheimer-Volkoff limit, as this maximum mass has come to be known, emerges from a fundamental competition between gravitational attraction and quantum pressure. As more mass is added to a neutron star, its gravitational field becomes stronger, compressing the interior to higher and higher densities. Initially, this compression increases the neutron degeneracy pressure, which provides additional support against further collapse. However, general relativity introduces a crucial and counterintuitive modification to this simple picture. In Einstein's theory of gravity, pressure itself contributes to the gravitational field. It acts as a source of space-time curvature, just like mass and energy do. This means that the very pressure that is supporting the neutron star against collapse is also enhancing the gravitational field that is trying to crush it. As the neutron star becomes more massive and the interior pressure increases, this relativistic effect becomes increasingly important. Eventually, it leads to a situation where adding more pressure actually makes gravitational collapse more likely, not less. The exact value of the maximum neutron star mass remains one of the most important unsolved problems in astrophysics. Current theoretical estimates place it in a range from about 2 solar masses to perhaps 3 solar masses. This wide range depends entirely on the assumed properties of ultra-dense matter. This uncertainty is a direct reflection of our incomplete understanding of how matter behaves at densities far exceeding those found in atomic nuclei, a realm where the familiar rules of nuclear physics may break down entirely. Recent astronomical observations have started to narrow down this possible range by discovering neutron stars that are increasingly massive. For example, the pulsar identified as PSRJ 0614-2230 was found to have a precisely measured mass of 1.97 solar masses. This discovery set a solid lower limit on what the maximum possible mass could be. Even more recently, another pulsar, designated PSRJ 0740 + 6620, has been measured. its mass was determined to be 2.14 solar masses, pushing that lower boundary even higher. These massive neutron stars place extremely important constraints on the equation of state of ultra-dense matter. Any theoretical models that predict a maximum mass below these observed values can be confidently ruled out. This eliminates many theoretical possibilities for exotic matter phases existing in neutron star cores. The potential existence of neutron stars with masses approaching 2.5 solar masses, if such an object is confirmed by future observations, would place even stronger constraints on fundamental physics. The process of gravitational collapse, once that maximum mass threshold is crossed, is both rapid and irreversible. When additional matter is added to a neutron star that is already near its maximum sustainable mass, the transition to a black hole can occur in a matter of milliseconds. Unlike the gradual evolution that is typical of most astrophysical processes, this collapse represents a genuine phase transition where the fundamental character of the object changes instantly. During this collapse, the neutron star's radius shrinks dramatically, while its mass remains approximately constant. The surface gravity increases without bound as the radius approaches the Schwarzschild radius. This is the critical size below which nothing, not even light, can escape the gravitational pull. Time dilation effects become extreme. For any hypothetical observer on the collapsing surface, time would appear to slow down drastically. The formation of an event horizon marks the point of no return in this collapse process. The event horizon is not a physical surface that you could touch. Rather, it is a boundary in spacetime. Beyond this boundary, no causal influence can propagate to external observers. Once matter crosses this boundary, it becomes forever disconnected from the outside universe. From the perspective of distant observers, it disappears from view due to the extreme gravitational time dilation. Neutron star mergers provide natural laboratories for studying this collapse threshold in action. When two neutron stars spiral into each other, they can temporarily form a hypermassive object. The total mass of this new object exceeds the maximum mass that can be supported by a single, non-rotating neutron star. These transient objects are stabilized for a short time by their rapid rotation and by intense thermal pressure. However, they must eventually collapse to form black holes as they lose energy through gravitational wave emission and cool down through neutrino radiation. The lifetime of these hypermassive neutron stars, how long they can exist before collapsing, depends very sensitively on their mass and on the equation of state of the matter in their cores. Objects that are only slightly above the maximum mass threshold might survive for seconds or perhaps even minutes before they collapse. In contrast, those with much higher masses will collapse almost immediately after they are formed. This survival time directly affects the electromagnetic signals associated with the neutron star merger. It influences the brightness and the duration of the kilonova and the properties of any gamma-ray bursts that might be produced. Observations of short gamma-ray bursts have provided indirect evidence for the formation of black holes through this exact process of neutron star collapse. These are intense flashes of high-energy radiation that typically last for less than 2 seconds. They are thought to be powered by powerful jets of material launched from the vicinity of a newly formed, rapidly spinning black hole. The observed association between short gamma-ray bursts and the gravitational wave signals from neutron star mergers strongly supports this interpretation and provides insights into the collapse process itself. The transition from a neutron star to a black hole involves dramatic changes in the geometry of spacetime around the object. The metric that describes spacetime around a neutron star, while strongly curved, still allows light and matter to escape from its surface. The black hole metric, by contrast, contains a region where spacetime curvature becomes so extreme that escape becomes impossible. This transition does not occur gradually. It happens as a sharp phase change, the instant the stellar radius drops below the critical Schwarzschild radius. Different theoretical models of the collapse process predict different observational signatures. If the collapse occurs very rapidly, any surface emission from the neutron star would be cut off abruptly as the event horizon forms. If, however, the collapse proceeds more gradually, there might be a period of intense heating and emission as matter is compressed to extreme densities right before it disappears behind the event horizon. The concept of gravitational mass limits extends beyond just neutron stars to other exotic objects that might exist in the universe. For instance, quark stars, hypothetical objects composed entirely of deconfined quark matter, would have their own maximum mass limits. These limits would depend on the properties of the quark matter equation of state. Some theoretical models suggest that quark stars might be able to support even higher masses than neutron stars, though this remains highly uncertain. Strange stars are another hypothetical object composed of absolutely stable, strange quark matter. These would obey different mass limits entirely. If strange matter is indeed more stable than normal nuclear matter, then the maximum mass for strange stars could be significantly higher than for neutron stars. However, the existence of strange stars remains purely speculative, with no confirmed observational evidence for such objects. The population of neutron stars that we observe near the maximum mass threshold provides important information about stellar evolution and supernova physics. The initial mass distribution of neutron stars depends on the properties of their progenitor stars and the precise details of the core collapse and explosion process. Therefore, understanding the distribution of neutron star masses offers insights into both stellar physics and the fundamental properties of matter. Gravitational wave observations have begun to constrain the maximum mass through studies of neutron star mergers. The inspiral signals, the waves emitted as they circle each other, encode information about the individual masses of the merging neutron stars. The post-merger signals, the waves emitted after they collide, can reveal whether the remnant forms a stable neutron star or if it collapses to a black hole. Future gravitational wave detectors with improved sensitivity may one day be able to observe the collapse process directly. The stability of neutron stars near this maximum mass limit can also be affected by external factors, such as accretion or the evolution of their magnetic fields. A neutron star that is perfectly stable in isolation might become unstable if it accretes or pulls in additional matter from a companion star. This process could explain some observations of black hole formation in X-ray binary systems, where the compact object appears to have grown in mass over time. Magnetic fields also complicate the analysis of maximum mass limits. This is because they provide an additional source of pressure support that can help stabilize neutron stars against gravitational collapse. Very strongly magnetized neutron stars, those we call magnetars, might be able to support slightly higher masses than their non-magnetized counterparts. However, the enormous energy stored in such strong magnetic fields would eventually decay, and this decay could potentially trigger a delayed collapse to a black hole. Rotation also affects the maximum mass that neutron stars can support. Rapidly rotating neutron stars experience powerful centrifugal forces. These forces partially offset the pull of gravitational attraction, allowing them to support higher masses than non-rotating stars. The The maximum mass for a rapidly rotating neutron star can be 20 to 30% higher than for a static star with the same equation of state. However, neutron stars cannot rotate arbitrarily fast. Eventually, the centrifugal forces would overcome gravitational attraction and tear the star apart. The maximum rotation rate depends on the neutron star's mass and radius, creating a complex relationship between mass, rotation, and stability. Some neutron stars might exist in a metastable state, where they are stable against collapse, but are unstable against spinning down. As they lose rotational energy, this spin down could eventually trigger a collapse. The study of neutron star oscillations provides another window into understanding stability and mass limits. These oscillation modes are analogous to seismic waves in planets. Their frequencies depend on the neutron star's mass, its radius, and its internal structure. As a neutron star approaches the maximum mass limit, certain oscillation modes can become unstable, potentially triggering a collapse even if the star would otherwise be stable. Future observations will likely refine our understanding of the maximum mass limit through several approaches. Improved gravitational wave detectors will observe many more neutron star mergers and provide better constraints on the equation of state. More sensitive radio telescopes will discover additional massive pulsars, extending the known range of measured neutron star masses. Advanced X-ray telescopes will study the thermal evolution and surface properties of neutron stars across a wide range of masses. The discovery of a neutron star with a mass significantly above our current theoretical limits would represent a revolutionary finding. It would require completely new physics to explain. Such an observation might indicate the existence of new forms of matter that provide additional pressure support, or it could even suggest that our understanding of gravity itself needs to be modified in these extreme environments. Conversely, the observation of a sharp cutoff in the neutron star mass distribution would provide strong evidence for the existence of a maximum mass limit. This would help to constrain the equation of state of ultra-dense matter. The shape of this cutoff, whether it is sharp or gradual, would reveal information about the stability of neutron stars near that threshold and the dynamics of the collapse process itself. The collapse threshold represents more than just an astrophysical curiosity. It embodies the fundamental limits that the laws of physics impose on the structure of matter and spacetime. At this boundary, quantum mechanics makes its final stand against the inexorable pull of gravity. The outcome of that battle determines whether matter can exist in a stable form or whether it must surrender to the ultimate gravitational embrace of a black hole. Understanding this threshold requires bringing together insights from nuclear physics, quantum field theory, general relativity, and observational astronomy. Each advance in any of these fields contributes to our growing knowledge of where this boundary lies and what physical processes determine its location. As our theoretical understanding improves and our observational capabilities advance, we continue to probe ever closer to this fundamental limit, the point where matter gives way to pure space-time curvature. The collapse threshold thus stands as one of the most profound boundaries in all of physics. It marks the transition between objects that can be observed and studied directly and those that hide their secrets forever behind event horizons. It represents gravity's ultimate victory, the point where the curvature of spacetime becomes so extreme that it overwhelms all other forces and consumes matter itself into the darkness of a black hole. In the pantheon of cosmic laboratories, neutron stars stand as perhaps the most extraordinary testing grounds for our fundamental theories of physics. These collapsed stellar cores create gravitational environments so extreme that they probe regimes of space-time curvature that are completely inaccessible to any earthbound experiment. Within their vicinity, Einstein's theory of general relativity faces its most stringent tests. Alternative theories of gravity reveal their predictions, and the very foundations of our understanding of space, time, and matter are pushed to their absolute limits. The importance of neutron stars as gravitational laboratories stems from their unique position in the cosmic hierarchy of dense objects. They are compact enough to generate gravitational fields that approach the maximum possible strength, while still remaining stable against collapse into black holes. Unlike black holes, whose interiors are forever hidden behind event horizons, neutron stars allow for the direct observation of matter and energy operating under extreme gravitational stress. This accessibility makes them invaluable for testing theoretical predictions that would otherwise remain purely speculative. Einstein's theory of general relativity has withstood every single experimental test that has been devised since its formulation over a century ago. These tests range from the bending of starlight observed during solar eclipses to the direct detection of gravitational waves from colliding black holes. Yet, most of these tests have probed relatively weak gravitational fields, where space-time curvature remains modest and the deviations from Newtonian gravity are small. Neutron stars, however, operate in the strong field regime. This is where general relativity makes predictions that differ dramatically from those of alternative theories. The precision timing observations of pulsars provide some of the most accurate tests of general relativity ever performed. The millisecond pulsars, which are neutron stars rotating hundreds of times every second, maintain a timing stability that rivals the very best atomic clocks on Earth. This extraordinary precision allows astronomers to detect minuscule deviations in the arrival times of their pulses. These deviations reveal the effects of gravitational time dilation, the curvature of space, and the emission of gravitational waves. Binary pulsar systems offer particularly powerful tests. This is because they create dynamic gravitational environments where the space-time curvature is continuously changing as the two neutron stars orbit each other. The famous Hulse-Taylor binary pulsar provided the very first confirmation of gravitational wave emission. The observed orbital decay of that system matched Einstein's predictions to within a few parts in 10,000. More recent discoveries of double pulsar systems have pushed the precision of these tests to even greater levels. The double pulsar system, PSRJ-0 737-3039, represents the ultimate laboratory for testing general relativity in the strong field regime. This remarkable system contains two active pulsars orbiting each other with a period of just 2.4 hours. This setup allows astronomers to observe relativistic effects from both neutron stars simultaneously. The system exhibits multiple relativistic effects: orbital precession, gravitational time dilation, the Shapiro delay, and orbital decay due to gravitational wave emission. All of these effects can be measured with extraordinary precision. Each of these relativistic effects provides an independent test of Einstein's theory. The orbital precession occurs because the elliptical orbit slowly rotates in space. This is a direct result of the curvature of space-time around the massive neutron stars. The rate of this precession depends on the total mass of the system and provides a direct measurement of how matter curves space-time in the strong field regime. Gravitational time dilation becomes measurable in these systems because the neutron stars experience varying gravitational potentials as they move through their elliptical orbits. When a pulsar is closer to its companion, it experiences a stronger gravitational field. This causes its internal clock to run slower relative to distant observers. This effect creates periodic variations in the observed pulse rates that can be detected through long-term timing observations. The Shapiro delay effect occurs when the radio pulses from one pulsar pass through the curved spacetime near its companion on their way to Earth. The gravitational field of the companion neutron star actually increases the travel time of these radio signals. This creates a measurable delay that depends on the companion's mass and the geometry of the orbit. This effect provides yet another independent constraint on the system's parameters and a powerful test of general relativity. Perhaps most remarkably, the orbital decay of binary pulsar systems caused by the emission of gravitational waves has been confirmed to match Einstein's predictions with incredible precision. As the neutron stars orbit each other, they generate ripples in spacetime that carry away energy. This energy loss causes the orbit to shrink gradually over time. The rate of this orbital decay can be predicted exactly from general relativity and then compared with decades of timing observations. The agreement between theory and observation in these binary pulsar tests is truly extraordinary. The orbital decay of the Hulse-Taylor pulsar matches the general relativistic prediction to better than 1 part in 10,000. The double pulsar system shows even better agreement. These tests are probing general relativity in gravitational fields that are billions of times stronger than those accessible to any solar system experiments. Alternative theories of gravity face severe constraints from these pulsar observations. Many modified theories, which attempt to explain cosmological mysteries like dark matter or dark energy by changing the laws of gravitational physics, predict deviations from general relativity. These deviations should be detectable in strong field environments. The precise agreement between pulsar observations and Einstein's predictions effectively rules out large classes of these alternative theories. For example, scalar tensor theories, which include additional fields beyond the standard metric tensor of general relativity, predict violations of the strong equivalence principle. These violations should be observable in neutron star systems. These theories typically predict that the gravitational binding energy of a neutron star should affect how it responds to external gravitational fields. This would lead to orbital anomalies in binary systems. The fact that we observe no such anomalies in pulsar systems places tight constraints on these scalar tensor theories. Extra-dimensional theories, which are motivated by string theory and other approaches to quantum gravity, often predict modifications to general relativity at high energies or in strong gravitational fields. Neutron stars, with their extreme densities and gravitational fields, provide natural testing grounds for these modifications. So far, no deviations from general relativity have been detected, which constrains the parameter space of these extra-dimensional models. Some theories predict the existence of additional gravitational degrees of freedom. These could lead to something called dipole gravitational radiation, a form of energy loss that is not present in general relativity. If such radiation existed, binary pulsar systems would lose energy faster than predicted by Einstein's theory. The precise match between the observed and predicted orbital decay rates rules out dipole radiation and constrains the theories that predict its existence. The neutron stars themselves also serve as laboratories for testing the strong equivalence principle. This is one of the fundamental assumptions that underlies all of general relativity. This principle states that all forms of matter and energy respond identically to gravitational fields, regardless of their internal structure or composition. Neutron stars, with their exotic compositions and extreme internal binding energies, provide crucial tests of this very principle. The gravitational binding energy of a neutron star, the energy holding it together, represents a significant fraction of its total mass energy. This is unlike ordinary matter, where binding energies are negligible. If the strong equivalence principle were violated, this binding energy might respond differently to external gravitational fields. This would lead to anomalous accelerations of neutron stars in binary systems. The precise orbital motion of binary pulsars confirms that neutron stars fall in external gravitational fields exactly as the equivalence principle predicts they should. Different neutron star compositions would test the equivalence principle in different ways. A neutron star containing exotic matter, like strange quarks or hyperons, would have different binding energy contributions than a star composed purely of normal nucleons. Comparing the orbital behavior of neutron stars with different masses and presumably different compositions provides additional tests of the equivalence principle in the strong field regime. The moment of inertia of neutron stars provides another avenue for testing gravitational physics. General relativity makes specific predictions about how the moment of inertia relates to the mass and radius of a neutron star. These predictions differ from those of many alternative theories. Measuring neutron star moments of inertia, perhaps through observations of geodetic precession in binary systems, could reveal deviations from Einstein's theory. Gravitational wave observations have opened up entirely new possibilities for testing general relativity using neutron stars. The LIGO and Virgo detectors have observed gravitational waves from neutron star mergers. This provides direct confirmation of Einstein's predictions about how space-time itself propagates disturbances at the speed of light. These observations test general relativity in the most dynamic and extreme gravitational environments ever observed. The inspiral phase of neutron star mergers probes the two-body dynamics of strongly gravitating objects. It tests whether Einstein's equations correctly predict the orbital evolution as the neutron stars spiral toward each other. The merger phase tests general relativity in the most extreme conditions, where space-time curvature reaches values comparable to those near a black hole's event horizon. Future gravitational wave observations will provide even more stringent tests of gravitational physics. Third-generation detectors, like the Einstein telescope, will be sensitive enough to observe neutron star oscillations. They may also be able to detect post-Newtonian corrections to the gravitational wave signal that would reveal subtle deviations from general relativity. The polarization of gravitational waves provides another test of Einstein's theory. General relativity predicts that gravitational waves should exhibit only two polarization states. These correspond to the two independent ways that spacetime can be stretched and compressed. Alternative theories often predict additional polarization modes. These could be detected by a network of gravitational wave detectors with different orientations on Earth. Tests of Lorentz invariance, the principle that the laws of physics are the same in all inertial reference frames, can be performed using pulsar timing observations. Any violation of Lorentz invariance would cause the travel time of radio pulses to depend on their frequency or their direction of propagation. The extraordinary timing precision of millisecond pulsars makes them sensitive to Lorentz violation effects that would be completely undetectable in any other system. Some theories of quantum gravity predict modifications to general relativity that become important near the Planck scale, the scale where quantum effects on spacetime itself become significant. While neutron stars do not approach Planck scale densities, they do probe energy scales and gravitational fields that are much, much higher than those accessible to laboratory experiments. Any quantum corrections to general relativity might therefore be detectable, in principle, in high-precision neutron star observations. The study of neutron star populations across cosmic time also provides tests. It allows us to check whether the fundamental constants of physics, including Newton's gravitational constant g, have remained truly constant throughout the universe's history. Any changes in these constants would affect neutron star formation rates, their maximum masses, and their cooling evolution in ways that might be detectable through large surveys of neutron star properties at different redshifts or distances. Neutron stars also provide laboratories for testing the interaction between gravity and the other fundamental forces. The extreme magnetic fields of magnetars, which reach strengths of 10 to the 15th Gauss, create environments where electromagnetic and gravitational effects become comparable in strength. Understanding how these forces interact in such extreme conditions requires precision tests, which neutron stars uniquely provide. The cooling evolution of neutron stars offers insights into how gravity affects particle physics processes in extreme environments. Different neutrino emission mechanisms, some of which may depend on gravitational effects, like the coupling between gravitational and weak nuclear forces, produce characteristic cooling signatures. These signatures can be observed by X-ray telescopes. Some theories of modified gravity predict that neutron stars should exhibit a different thermal evolution than what general relativity predicts. These theories often include new scalar fields that can affect the interaction between matter and radiation, potentially altering cooling rates or surface emission properties in detectable ways. As observational techniques continue to improve and new theoretical frameworks emerge, neutron stars will undoubtedly continue to serve as crucial testing grounds for our understanding of gravity and fundamental physics. Each new measurement of a neutron star property, whether it comes through electromagnetic observations or gravitational wave detections, provides another data point for testing the very foundations of modern physics. The unique combination of extreme gravitational fields, precise observational techniques, and long-term stability makes neutron stars irreplaceable laboratories. They are essential for probing the deepest questions about the nature of space, time, and gravity. They represent natural experiments that operate at energy scales and field strengths that may never be accessible to human technology. They provide our best hope for discovering new physics beyond the standard model of particle physics and general relativity. In this vital role as cosmic laboratories, neutron stars continue to validate Einstein's remarkable theory. At the same time, they are diligently searching for hints of new physics that might guide us toward a more complete understanding of the universe. They stand as monuments to the power of precision observation and theoretical prediction, demonstrating how the most extreme environments in nature can illuminate the most fundamental laws that govern reality itself. In the vast cosmic theater, where galaxies spiral through space and stars are born and die in spectacular fashion, neutron stars stand as perhaps the universe's most paradoxical objects. They are, at the same time, the smallest and yet the most massive stars. They are the quietest and the most energetic beacons. They are the most stable and the most violent remnants of stellar death. These cosmic lighthouses pulse with mechanical precision across billions of years. Yet, they harbor in their cores some of the most extreme physics imaginable. They create a bridge between the quantum realm of subatomic particles and the grand stage of general relativity. As we reach the end of our journey through the gravitational wonderland of neutron stars, it becomes clear that these objects represent far more than mere astronomical curiosities. They are, in fact, cosmic laboratories where the fundamental forces of nature are pushed to their absolute limits. They are natural experiments that probe regimes of physics completely inaccessible to any earthbound science. And they are precise timepieces that allow us to test our most cherished theories about the nature of space, time, and matter. What we know about neutron stars reads like a catalog of extremes, a list of properties that challenge human comprehension. We know that they contain more mass than our own sun, yet are compressed into spheres smaller than many cities. This creates surface gravities so intense they would flatten mountains to mere centimeters in height. We know their magnetic fields can be trillions of times stronger than Earth's, powerful enough to disrupt atomic structure itself and to launch charged particles to velocities approaching the speed of light. We know they rotate with the stability of atomic clocks, while simultaneously generating gravitational waves that ripple through the very fabric of space-time. We understand that their crusts consist of crystalline lattices made of exotic nuclei, arranged in phases that have been playfully dubbed nuclear pasta. Meanwhile, their cores may harbor forms of matter that exist nowhere else in the entire universe. We have measured their masses with extraordinary precision using pulsar timing. We have mapped their surfaces using the effects of gravitational light bending. And we have witnessed their cataclysmic collisions by using gravitational wave detectors, incredible instruments that are so sensitive they can sense distortions in spacetime that are smaller than 1/10,000th of the width of a single proton. Yet, for all of our accumulated knowledge, neutron stars continue to guard many of their deepest secrets. The precise nature of matter at the highest densities remains uncertain. The theoretical possibilities range from superfluids of neutrons to exotic soups of deconfined quarks and strange matter. The maximum mass that these objects can achieve before they collapse into black holes depends sensitively on physics that we do not yet fully understand. This leaves open fundamental questions about the ultimate fate of matter when it is subjected to extreme gravitational stress. The equation of state, the rule that describes how pressure relates to density deep in neutron star cores, represents one of the greatest unsolved problems in modern physics. Despite decades of theoretical work and increasingly sophisticated experiments, we cannot yet predict from first principles whether a neutron star with twice the Sun's mass should have a radius of 10 kilometers or 15 kilometers. This uncertainty reflects our incomplete understanding of how the strong nuclear force behaves when nucleons are compressed far beyond the densities found in normal atomic nuclei. Future observations promise to narrow these uncertainties through multiple complementary approaches. Gravitational wave detectors will observe larger numbers of neutron star mergers. This will provide statistical constraints on the population properties and on their tidal deformabilities, which encode information about their internal structure. Advanced X-ray telescopes will map their surface emissions with greater precision, revealing new details about magnetic field configurations and thermal evolution. Radio telescopes of unprecedented sensitivity will discover new populations of pulsars and measure their properties with ever greater accuracy. The next generation of gravitational wave detectors, with sensitivities improved by orders of magnitude, may be able to observe neutron star oscillations directly. This would open the field of gravitational wave asteroseismology. Just as seismic waves reveal the internal structure of the Earth, these stellar oscillations would provide direct probes of neutron star interiors. They could potentially distinguish between different phases of ultra-dense matter and reveal the presence of exotic particles or phase transitions. Perhaps most intriguingly, future observations may detect the boundaries where neutron star physics transitions into even more exotic regimes. We may one day witness the formation of quark stars. We might observe strange matter in neutron star cores, or we might detect the signatures of quantum phase transitions that occur nowhere else in nature. Each new discovery will add another piece to the puzzle of understanding how matter behaves when it is compressed beyond the limits of all terrestrial experience. The role of neutron stars in advancing fundamental physics extends far beyond their use as laboratories for studying ultra-dense matter. They also serve as precision instruments for testing general relativity in regimes where space-time curvature approaches its maximum possible values, while still allowing stable matter to exist. The extraordinary agreement between pulsar timing observations and Einstein's predictions has validated general relativity in these strong field regimes and has severely constrained alternative theories of gravity. As we search for new physics beyond the standard models of particle physics and cosmology, neutron stars will undoubtedly continue to play crucial roles. They may reveal evidence for extra dimensions. They might show us quantum corrections to general relativity, or even violations of fundamental symmetries that could guide us toward more complete theories of nature. The precision of pulsar timing observations and the extreme conditions found in neutron star cores make them sensitive to effects that would be completely undetectable in any Earth-bound experiment. Neutron stars also represent a remarkable convergence of different fields of physics. They bring together insights from nuclear physics, quantum field theory, condensed matter physics, plasma physics, and general relativity. Understanding these objects fully requires bridging the gap between the quantum mechanical behavior of individual particles and the macroscopic properties of stellar objects. It requires connecting the microscopic world of quarks and gluons to the cosmic scale of space-time curvature and gravitational waves. The study of neutron stars has already led to numerous unexpected discoveries that have reshaped our understanding of physics and astronomy. The discovery of pulsars themselves was completely unanticipated. It revealed the existence of cosmic lighthouses with a timing precision that surpasses our best atomic clocks. The observation of binary pulsars provided the very first evidence for gravitational waves, decades before their direct detection. This achievement earned Nobel Prizes and validated one of Einstein's most abstract predictions. More recently, the detection of gravitational waves from neutron star mergers has opened the era of multi-messenger astronomy. This allows us to study cosmic events through both gravitational and electromagnetic radiation simultaneously. These observations have confirmed that neutron star collisions are major sites of heavy element synthesis. This solved long-standing puzzles about the cosmic origins of gold, platinum, and other precious metals. Each neutron star merger we observe adds to our understanding of how these events shape the chemical evolution of galaxies. They help us understand how they contribute to the cosmic abundance of elements that are essential for planet formation and for life itself. The gravitational wave signals from these mergers encode information about the equation of state of matter at nuclear density, providing constraints that complement laboratory experiments and theoretical calculations. As we look toward the future, neutron stars will likely continue to surprise us with unexpected phenomena and new physics. The extreme conditions in their cores may give rise to phases of matter that we have not yet even imagined. Their powerful magnetic fields and rapid rotation may create plasma physics phenomena that challenge our current understanding. The interaction between quantum mechanics and general relativity in these extreme environments may reveal new insights into the long-sought theory of quantum gravity. The precision timing capabilities of pulsar arrays may eventually allow us to detect the background hum of gravitational waves from the early universe. This would provide a new window into cosmic history, complementing observations of the cosmic microwave background. Neutron stars may thus serve not only as laboratories for studying extreme physics, but also as instruments for exploring the deepest questions about the origin and evolution of the universe itself. Perhaps most remarkably, neutron stars embody the profound connection between the largest and the smallest scales in physics. These objects, with masses comparable to stars and sizes comparable to cities, are governed by quantum mechanical effects that operate on subatomic scales. The Pauli exclusion principle, a purely quantum phenomenon involving the behavior of individual fermions, is what determines the structure and stability of objects containing more matter than our entire Sun. This quantum gravitational interplay represents one of the most striking examples of how the microscopic and macroscopic worlds are interconnected in nature. Neutron stars demonstrate that quantum mechanics is not just a theory for describing atoms and molecules. It is a fundamental principle that shapes the cosmos on astronomical scales. They stand as monuments to the unity of physics, showing how seemingly disparate phenomena are all connected by common, underlying principles. The quiet precision of pulsar signals, arriving at Earth with clockwork regularity across distances of thousands of light-years, provides a constant reminder of the extraordinary stability and predictability that can emerge from the most violent and chaotic processes in nature. These beacons sweep across space with lighthouse-like regularity. Each pulse represents a complete rotation of a neutron star that is spinning hundreds of times per second, all while maintaining a timing precision that rivals our best atomic clocks. In their role as cosmic timekeepers, neutron stars serve as both clocks and beacons in the warped fabric of space-time. They mark the passage of time with extraordinary precision, while simultaneously demonstrating how gravity can bend and distort the very flow of time itself. Each pulse that reaches Earth has had to climb out of a gravitational well so deep that its wavelength is stretched by the journey. It carries with it information about the extreme conditions near the neutron star's surface. The legacy of neutron stars extends beyond their contributions to fundamental physics and astronomy. They represent one of humanity's greatest intellectual achievements. They demonstrate our ability to understand and predict phenomena that occur under conditions so extreme that they challenge the very limits of physical theory. From the initial theoretical prediction of their existence back in the 1930s, all the way to the direct detection of their gravitational wave signals in the 21st century, neutron stars have consistently driven advances in both theoretical understanding and observational capability. As we stand at the threshold of even more advanced gravitational wave detectors, more sensitive radio telescopes, and more powerful X-ray observatories, neutron stars will undoubtedly continue to reveal new secrets about the nature of matter, energy, space, and time. They remain our best natural laboratories for studying physics under extreme conditions. They are our most precise clocks for testing theories of gravity. And they are our most promising sources of information about the behavior of matter at densities that may never be achievable in terrestrial experiments. In the end, neutron stars represent both the triumph of theoretical physics in predicting their existence and properties, and the ongoing challenge of understanding all the mysteries they continue to present. They are the products of stellar death that give birth to new insights about the nature of life and matter in the universe. They are the quiet titans of gravity, spinning silently through space while harboring in their cores some of the most extreme and exotic physics imaginable. These remarkable objects will continue to serve as beacons of discovery, guiding us toward a deeper understanding of the fundamental laws that govern our universe. In their precise pulses and their extreme physics, we find both answers to long-standing questions and hints of new mysteries that are yet to be unraveled. They remind us that even in the vastness of the cosmos, precision and beauty can emerge from chaos and violence. They create natural laboratories where the most profound secrets of physics await our discovery. The story of neutron stars is far from over. As our observational capabilities advance and our theoretical understanding deepens, these cosmic laboratories will undoubtedly reveal new phenomena that challenge our current knowledge and point toward even more fundamental truths about the nature of reality itself. In their quiet spinning and precise timing, neutron stars continue to whisper the secrets of gravity, matter, and space-time. To anyone patient enough to listen to their cosmic song,